Hello and welcome. I'm so glad you're here with me tonight. Find a comfortable position wherever you are. Let your shoulders drop, release any tension you might be holding in your jaw, and take a slow, deep breath. Hold it for just a moment, then now let it go. Tonight we're going on a journey together, a peaceful exploration into one of the most beautiful and fundamental concepts in all of mathematics. We're going to discover how polynomials, these elegant mathematical expressions, are woven into the very fabric of our universe. But don't worry if mathematics hasn't always been your favorite subject. Tonight there are no tests, no pressure, no rushing. We're simply going to wander through ideas together, at a pace that feels calm and natural. Think of this time as a gift you're giving yourself, a chance to let your mind drift through the cosmos of mathematical thought, to see patterns and connections that have been hiding in plain sight all along. Tonight we're going to explore something that's been hiding in plain sight, something so fundamental to the universe that it's written into the fabric of everything around us. We're going to talk about polynomials, about exponentials, about e raised to itself again and again, and we're going to discover that these aren't just mathematical abstractions. They're the language that nature whispers in the dark. Think of this as a journey through crystalline frost blooming in eternal silence, where each mathematical truth unfolds like gossamer wings catching fragments of starlight. We'll move gently from one idea to the next, letting the patterns reveal themselves in their own time. What we're going to explore tonight starts with a simple question that leads us into obsidian depths breathing, with bioluminescent wonder. Why do polynomials work so well? Why can we approximate nearly anything in mathematics with these simple sums of powers? And what happens when we take e, that mysterious number that appears everywhere in nature, and raise it to itself, and then raise that to itself, and keep going? The answers lead us to exponential functions, to power series, to the very structure of growth and decay in our universe. But more than that, they lead us to understand why mathematics feels the way it does, why certain patterns repeat across completely different domains, why the same shapes appear in spirals of galaxies, and the curves of seashells. So let's begin with polynomials, those gentle creatures built from nothing more than addition, multiplication, and whole number powers. Let's see how they become bridges between the simple and the infinite, how they connect discrete steps to continuous flows, how they transform the abstract into something we can touch and understand. The night is long, the mathematics is deep, and we have time to explore it all. Imagine you're standing in a luminous garden suspended between dreams and waking, and you're trying to describe the curve of a path through it. Not with images, not with gestures, just with numbers. This is what polynomials let us do. They're descriptions of curves, of shapes, of relationships, written in the most elementary language mathematics has. A polynomial is just a sum of terms, each term a number times x raised to some power. You might have 5 plus 3 times x plus 2 times x squared. That's a polynomial. The powers have to be whole numbers, 0 or 1 or 2 or 17, and each term is just a coefficient, a number, multiplying that power of x. The beauty here, the thing that makes polynomials special, is their simplicity, combined with their power. You can add them together easily, multiply them, and you get another polynomial. Differentiate them and they stay polynomials, just simpler ones. They're closed under all the basic operations we care about, like velvet midnight wrapped in silver threads, self-contained and complete. But there's something deeper happening. Polynomials are how we approximate everything else. Want to understand sine and cosine? Build them from polynomials. Want to understand e raised to x? Build it from polynomials. Want to understand logarithms, square roots, anything that curves and bends? Start with polynomials. This is where Taylor series enter, those infinite sums that let us write any smooth function as a polynomial that goes on forever. Think of it like this. You're standing at a point on a curve, and you want to predict what the curve does nearby. First approximation is a constant, just the value at that point. Second approximation adds a line, capturing the slope. Third approximation adds a parabola, capturing the curvature. Fourth adds how the curvature is changing, and on, each term in your polynomial capturing another layer of behavior, another degree of subtlety. For the exponential function, e raised to x, this process reveals something extraordinary. The Taylor series centered at 0 starts with 1 plus x squared over 2 factorial plus x cubed over 6 factorial, continuing forever. Each coefficient is 1 over n factorial, where n is the power of x. Now here's where things get interesting, where we move into territory like iridescent waves breaking against forgotten shores. What is e itself? The number e is defined as e raised to 1, which means we can find it by plugging 1 into our series. We get 1 plus 1 plus 1 over 2 plus 1 over 6 plus 1 over 24, and so on forever. This sum converges to approximately 2.718, but the exact value is this infinite series, this infinite polynomial evaluated at 1. When we raise e to itself, we're taking this number, roughly 2.718, and using it as an exponent. E raised to e is about 15.15. Already we're in interesting territory. This number appears in various growth problems, in certain optimization scenarios, in places where natural growth compounds upon itself. But what if we keep going? What if we compute e raised to the quantity e raised to e? Now we're stacking exponentials, creating what mathematicians call a power tower. Each level of the tower is e raised to everything below it. For 3 e's we get e raised to approximately 15.15, which is approximately 3,200,000. The numbers explode upward with each level we add. This might seem like an abstract game, but power towers appear in real mathematics, in real science. They show up in complex analysis, in number theory, in models of certain chemical reactions where catalysis creates feedback loops. They're examples of tetration, the operation beyond exponentiation, just as exponentiation is beyond multiplication. Let's think about why exponentials are so important in the first place. In bronze autumn melting into indigo twilight, we can consider growth. When something grows exponentially, its rate of growth is proportional to its current size. Bacteria dividing, money compounding, nuclear reactions cascading, all follow this pattern. The differential equation is di over dx equals k times y, and the solution is y equals some constant times e raised to kt. This is why e appears everywhere in nature. It's not that nature chose e specifically, it's that e is what falls out when you solve the most fundamental growth equation. The exponential function e raised to x is the unique function that has its own derivative, that grows at a rate equal to its current value. When we raise e to e, we're asking about growth that itself is growing exponentially. When we raise e to e, we're asking about growth of growth of growth. The tower becomes a metaphor for compounding processes, for feedback loops, for systems that amplify themselves at every level. Now let's connect this back to polynomials through Taylor series. Remember that e raised to x equals the infinite sum of x to the n over n factorial. This is a polynomial with infinitely many terms. When we substitute e for x, we get e raised to e equals the infinite sum of e to the n over n factorial. We can expand this. The first term is e to the 0 over 0 factorial, which is 1. The second term is e to the first over 1 factorial, which is just e. The third term is e squared over 2. The fourth term is e cubed over 6. Each term involves e raised to increasing powers, divided by increasing factorials. This series converges quickly because factorials grow faster than exponentials. Even though e to the n gets large, n factorial gets much larger, so the terms shrink. By the time we reach the 10th term, we're dividing e to the 10th, about 22,000, by 10 factorial, about 3.5 million. The term contributes less than 1% to the sum. The convergence of this series is an example of delicate chaos blooming in sepia tones. The terms individually grow wild, but their sum is tamed by the factorials, settling to a finite value we set to compute to arbitrary precision. If we want to compute e raised to e raised to e, we substitute the value of e raised to e into our Taylor series for e raised to x. Now x is approximately 15.15, and we compute the sum of 15.15 to the n over n factorial. The first few terms dominate. 15 to the 0 is 1. 15 to the first is 15. 15 squared over 2 is about 112. 15 cubed over 6 is about 562. The terms peak around the 10th or 20th term, then decline as factorial growth overtakes exponential growth. The sum converges to approximately 3,200,000, giving us the value of the third level of our power tower. Each time we add another e to the tower, we're performing the same operation. Take the previous value, substitute it into the Taylor series for e raised to x. Sum the infinite polynomial. The process is recursive, self-similar, like ethereal mist curling through a bend in marble halls, where each archway frames another identical archway receiving into infinity. Let's pause here and think about what polynomials are really doing. They're breaking down complicated functions into simple pieces. Each term x to the n is simple to understand, simple to compute, simple to differentiate or integrate. When we sum them, weighted by coefficients, we build complexity from simplicity. This is profoundly important because it means we can understand any smooth function by understanding polynomials. We can compute it by computing polynomial terms. We can approximate it by truncating the polynomial after finitely many terms. The whole edifice of calculus, of analysis, of applied mathematics, rests on this foundation. The Taylor series is one type of polynomial expansion. There are others. Fourier series expand functions as sums of sines and cosines. Chebyshev polynomials minimize approximation error in certain senses. Orthogonal polynomials arise in quantum mechanics, in probability theory, in numerical analysis. Each type has its own character, its own strengths, but all share this fundamental property of building the complex from the simple. Consider moving through a space like weathered stone singing songs of ancient time. Each polynomial term is like a note, a single frequency. When we combine them, we create harmony, melody, the full richness of a mathematical function. Just as music can be analyzed into constituent frequencies, functions can be analyzed into constituent polynomials. The exponential function e raised to x is special among all functions, because it's the simplest in a certain sense. Its Taylor series has the simplest possible coefficients, just 1 over n factorial. Every term is as simple as it could be, while still producing a non-trivial function. This simplicity is why e appears so often, why it's fundamental rather than arbitrary. When we raise e to e, we're composing the exponential function with itself. Function composition is a deep operation. It's how we build complexity in mathematics. Start with simple functions, compose them, get something richer. Compose again, richer still. Power towers are repeated composition of the exponential function with itself, using e as both the base and the exponent. This creates a kind of fixed point structure. If we computed an infinite power tower of e's, what would it converge to? Surprisingly, it diverges. The tower grows without bound. But if we use the smaller base, say the square root of 2, the infinite tower would converge to 2. This connects to the Lambert W function, which solves equations involving x equals a raised to x. The study of power towers leads into complex analysis, into questions about where these towers converge, how they behave as functions of the base and the height. Now let's think about what happens when we differentiate these expressions. Moving through sapphire echoes rippling through translucent air. Derivative of e raised to x is e raised to x. This self-reference is what makes the exponential function unique. It's the eigenfunction of the derivative operator. What's the derivative of e raised to x with respect to x? We need the chain rule. The outer function is e raised to something, which differentiates to itself times the derivative of the something. The something is e raised to x, which differentiates to e raised to x. So the derivative is e raised to x, t raised to x, times e raised to x. We can write this as e raised to the quantity x plus e raised to x. The derivative involves both x and e raised to x, appearing in the exponent. This is more complex than the original function, which makes sense. Composition generally increases complexity, and differentiation of compositions involves all the layers. For e raised to e raised to e raised to x, the derivative involves the chain rule applied twice. We get e raised to e raised to e raised to x times e raised to e raised to x times e raised to x. This can be written as e raised to a sum involving x, e raised to x, and e raised to e raised to x. The pattern continues. Each additional level in the power tower adds another factor to the derivative, another term in the exponential. The derivative of a power tower of height n involves all the levels of a power tower of height n-1. This recursive structure is beautiful. It shows how the tower is built from itself, how each level depends on all the levels below. It's like tangled vines of pearl and copper entwined, each strand supporting and supported by others. Integration is more subtle. The integral of e raised to x is just e raised to x plus a constant. But the integral of e raised to x is just e raised to x plus a constant. But we can't express it in terms of elementary functions. We need to define a new special function just for this purpose, or express it as an infinite series. This is common in mathematics. Differentiation is usually easier than integration. Differentiation is local, depends only on behavior near a point. Integration is global, depends on behavior over an interval. The exponential function is special in being easy to integrate, but compositions of exponentials quickly become intractable. Let's explore the series representation more deeply, entering a space like shadowed sanctuary glowing with soft phosphorescence. We know e raised to x equals the sum from n equals 0 to infinity of x to the n over n factorial. If we substitute y for x, where y is itself a function of x, we get e raised to y equals the sum of y to the n over n factorial. For y equals e raised to x, this gives us e raised to x equals the sum of parentheses e raised to n parentheses to the n over n factorial. We can expand e raised to x using its own Taylor series, so each term becomes a series nested inside another series. The first term is e raised to 0x to the 0 over 0 factorial, which is 1. The second term is e raised to 1x over 1, which expands to the sum of x to the k over k factorial. The third term is e raised to 2x squared over 2, which is e squared times the sum of x to the k over k factorial, all squared, then divided by 2. Each successive term gets more complex, involving higher powers of the series for e raised to x. When we multiply everything out and collect terms by powers of x, we get a single power series in x, representing e raised to x. The coefficient of x to the n in this series involves sums over partitions, over ways to distribute powers among nested sums. The combinatorics becomes rich and complex, like fractured mirror reflecting infinite cerulean skies, each shard containing the whole. These coefficients have interpretations in combinatorics, in the counting of certain structures. The exponential generating function e raised to x minus 1 counts, labeled connected graphs. The study of these series connect analysis to discrete mathematics, to graph theory, to the enumeration of combinatorial objects. For the third level, e raised to x, we'd nest the series one level deeper. The complexity grows, but the structure remains coherent. Each level is built from the level below, using the same operation, series composition, applied again. This kind of recursive structure appears throughout mathematics. Continued fractions, nested radicals, iterated functions, all share this property of self-similarity, of building the whole from copies of itself. Let's think about the geometric meaning of these functions. The graph of y equals e raised to x is a curve that starts near 0 for negative x, passes through 1 at x equals 0, and rises steeply for positive x. It's always increasing, always concave up, approaching infinity as x goes to infinity. The graph of y equals e raised to x is similar but steeper. For x equals 0, y equals e, about 2.7. For x equals 1, y equals e raised to e, about 15. For x equals 2, y is e raised to e squared, about 1700. The function explodes upward much faster than simple exponential growth. This is super exponential growth. Faster than any polynomial, faster than any exponential with fixed base. It's the kind of growth we see in Ackermann's function, in certain rapidly growing sequences, in the worst-case complexity of some algorithms. The function e raised to x grows even faster. By x equals 2, we're already in the millions. By x equals 3, the numbers are beyond astronomical. This is growth on a scale that's hard to comprehend, like silken darkness woven with threads of pale starlight, where each thread represents orders of magnitude. Why study such extreme growth? Because it appears in real problems. The time complexity of certain algorithms, the energy requirements of certain physical processes, the scales of certain cosmological phenomena, all involve super-exponential or faster growth. Understanding these functions helps us understand the limits of computation, the boundaries of what's physically possible. There's also pure mathematical beauty here. These functions are exactly as complex as they need to be to exhibit certain behaviors. They're the canonical examples of titration, of iterated exponentiation. They help us understand function spaces, growth hierarchies, the structure of mathematical operations. Let's consider the inverse question. If y equals e raised to x, can we solve for x? We need to take logarithms twice. First, the natural log of y gives e raised to x. Then the natural log of that gives x. So x equals log of y. This double logarithm grows incredibly slowly. While e raised to x explodes up log. Log of x grows so slowly it's almost flat. To go from log of x equals 0 to log of x equals 1, x has to go from 1 to e raised to e, about 15. To reach log of x equals 2, x has to reach e raised to e, about 3 million. The interplay between these extremely fast-growing and extremely slowly growing functions is profound, like emerald secrets hidden in layer fog and shadow. They're inverses, yet their behavior is so different, so extreme in opposite directions, that they seem to inhabit different mathematical universes. In complexity theory, the iterated logarithm appears in the analysis of algorithms. Some data structures have operations that take time proportional to log star of n. The iterated logarithm, the number of times you must take the log to reduce n to 1 or less. For all practical values of n, log star is at most 5. It grows so slowly it's essentially constant. Meanwhile, iterated exponentials appear in the analysis of very inefficient algorithms, or in counting problems where the answer grows faster than any polynomial or simple exponential. The gap between these scales is vast. Yet both are important for understanding the full spectrum of mathematical behavior. Now let's think about complex numbers, moving into luminescence blooming from the heart of forgotten worlds. The exponential function e raised to z for complex, z equals e raised to x, times parentheses, cosine of y, plus I, sine of y, end parentheses, where z equals x plus iy. This is Euler's formula generalized. The exponential function maps the complex plane to itself in a beautiful way. Vertical lines map to circles around the origin. Horizontal lines map to rays from the origin. The function is periodic in the imaginary direction with period 2 pi high. What happens when we compute e raised to z for complex z? The behavior becomes wild and intricate. The function has essential singularities, branch points, regions where it oscillates infinitely. Plotting the magnitude or phase creates images of stunning complexity, fractal-like structures, patterns within patterns. The iteration of e raised to z as a function of complex z is chaotic in the technical sense. Small changes in z lead to large changes in e raised to e raised to e raised to z. There's sensitive dependence on initial conditions, the hallmark of chaos. This connects to the study of complex dynamics, to Julia sets, and the Mandelbrot set, to the iteration of quadratic polynomials, and other functions. The exponential function, iterated or composed with itself, generates dynamics as rich as any in mathematics. For real values, we could ask about the stability of iteration. If we start with some x, and repeatedly apply the function f of t equals e raised to t, do we converge, diverge, or cycle? For x less than about 0.31, the iteration converges to a fixed point around 0.318. For x larger than this, iteration diverges to infinity. This critical value, where behavior changes from convergence to divergence, is itself interesting. It's related to the solution of x equals e raised to negative x, which connects to the Lambert W function again. If we iterated f of t equals e raised to t, the dynamics would be even more extreme. The function grows so fast that almost any starting point leads to rapid divergence. Only very special initial conditions might lead to convergence or bounded behavior. Let's return to polynomials and consider why they're the secret to mathematics. In obsidian depths breathing with bioluminescent wonder, we find that every smooth function can be approximated by polynomials. This is the Weierstrass approximation theorem. Given any continuous function on a closed interval and any desired accuracy, there exists a polynomial that approximates the function to that accuracy. This means polynomials are dense in the space of continuous functions. They're everywhere, can get arbitrarily close to anything. This is why numerical methods rely on polynomials. When we solve differential equations numerically, we approximate solutions with polynomials. When we interpolate data, we use polynomials. When we compress information, we often use polynomial representations. The FFT, fast Fourier transform, is about polynomial multiplication in disguise. Interpolation and evaluation of polynomials at special points, the roots of unity, gives us efficient algorithms for signal processing, for solving convolutions, for multiplying large numbers. Polynomials are algebraically closed in a beautiful way. The fundamental theorem of algebra says every non-constant polynomials has a root in the complex numbers. This means we can factor any polynomial completely over the complex numbers. This closure property makes polynomials tractable, understandable, complete. When we generalize to Laurent series, which allow negative powers of x, we get even more flexibility. When we generalize to power series in multiple variables, we can handle functions of several variables. When we generalize to formal power series, ignoring convergence, we get an algebraic structure useful in combinatorics in algebra. The ring of polynomials over a field is a fundamental object in algebra. Its properties, its ideals, its quotient rings, all have interpretations and applications. Algebraic geometry studies solution sets of polynomial equations, connecting algebra to geometry in profound ways. So when we study e raised to e, we're not just playing with numbers, we're exploring the boundaries of polynomial approximation, seeing where Taylor series lead when we push them to extremes. We're studying composition, iteration, recursion, the building blocks of complexity in mathematics. The fact that e raised to x has such a simple Taylor series, that it's its own derivative, that it appears in the solution to the most basic differential equation, all point to its fundamental nature. When we stack copies of e exponentially, we're exploring what happens when fundamental objects interact with themselves, when simplicity compounds into complexity. Think of each polynomial term as a whisper in the dark, a small contribution to the whole. The constant term 1 says where we start. The linear term x says how we initially change. The quadratic term, x squared over 2, says how the change itself changes. Each term adds nuance, adds detail, refines our approximation. For most functions, infinitely many terms are needed for perfect representation. But finite truncations give useful approximations. Engineers use low-degree polynomials to approximate trigonometric functions in calculators, to approximate square roots, to solve equations numerically. The truncation error, the difference between the true function and the polynomial approximation, can be bounded using the remainder term in Taylor's theorem. This remainder involves the next derivative evaluated at some point in the interval. For the exponential function, all derivatives equal the function itself, so the remainder is bounded by the function's maximum value. On the interval times, x to the n plus 1 over n plus 1 factorial, this bound decreases rapidly for fixed x, as n increases, which is why Taylor series for e raised to x converge quickly. The exponential function is entire, analytic, everywhere in the complex plane, which is why its Taylor series converges everywhere. For e raised to x, the function is still entire, still analytic, everywhere. But the coefficients of its Taylor series are more complex, grow faster, reflect the faster growth of the function itself. Let's think about applications where these ideas matter. In physics, exponential functions describe radioactive decay, population growth, charging capacitors, cooling objects. The differential equation for these processes is di over dx equals negative k times y, or plus k times y, with solution involving e raised to kt. When processes compound, when decay produces products that themselves decay at different rates, we get sums of exponentials, solutions involving multiple exponential terms with different rate constants. In finance, continuous compounding of interest leads to the formula A equals P times e raised to RT, where P is principal, R is rate, T is time. If the rate itself changes exponentially, perhaps due to inflation or economic growth, that feeds back on itself, we might get e raised to something. In chemistry, reaction rates often depend exponentially on temperature through the Arrhenius equation. The rate constant, K equals A, times e raised to negative e over RT, where E is activation energy, R is the gas constant, T is temperature. Catalytic cycles where products catalyze their own production can lead to super-exponential growth, limited eventually by depletion of reactants or other factors. In computer science, the time complexity of nested loops is often polynomial. A single loop over n elements is O of n. 2 nested loops are O of n squared. 3 nested loops are O of n cubed. But if each iteration spawns more iterations exponentially, we get exponential complexity. And if the exponent itself grows, we can get even worse complexity. The Ackermann function, which grows faster than any primitive recursive function, involves nested recursion that creates super-exponential growth. It's not computable in polynomial time or even exponential time. It represents a boundary of computational feasibility. So these mathematical structures, polynomials and exponentials, and their iterations, are not abstract curiosities. They're the patterns that govern growth, change, complexity in the real world. In a space like dark, starry, glossy essence, we can contemplate the philosophical implications. Mathematics is a language for describing patterns. Polynomials are sentences in that language, simple sentences built from basic grammar. Exponentials are a particular kind of pattern, a particular kind of sentence, that says growth proportional to current state. When we iterate these structures, compose them, nest them, we're exploring what the language can express. We're finding the boundaries of description, the limits of our mathematical vocabulary, and we find that even with simple building blocks, even with just addition and multiplication and exponentiation, we can describe growth so rapid it defies intuition. Functions so complex, they fill the complex plane with intricate structure, solutions to equations that require new special functions to express. This is the power of mathematics. From finite rules, infinite complexity emerges. From simple operations, profound depth arises. The polynomial x squared plus 1 seems trivial, but it defines the complex numbers when we ask for its roots. The exponential e raised to I times pi seems abstract, but it equals -1, connecting 5 of the most important constants in mathematics. Similarly, e raised to e seems like a curiosity, but it opens doors to tetration, to super-exponential growth, to iterated function systems, to dynamics and chaos, and the study of how simple rules generate complex behavior. Let's explore one more connection, moving through crystalline frost, blooming in eternal silence. The gamma function generalizes the factorial to non-integer values. For positive integers, n, gamma of n, equals n-1 factorial. But gamma can be defined for all complex numbers, except negative integers. The gamma function appears in the normalization of many probability distributions, in the solutions to certain differential equations, in number theory through its connection to the Riemann zeta function. Now consider the superfactorial, defined as the product of the first n factorials, 1 factorial, times 2 factorial, times 3 factorial, up to n factorial. This grows even faster than exponential, faster than factorial. It's related to the Barnes G function, a cousin of the gamma function. And there are even faster growing sequences. The exponential factorial is n raised to n-1, raised to n-2, raised to ... raised to 2 raised to 1. This is a power tower built from decreasing integers. For n equals 3, it's 3 raised to 2 raised to 1, which equals 3 squared, which equals 9. For n equals 4, it's 4 raised to 3 raised to 2 raised to 1, which is 4 raised to 3 squared, which is 4 raised to 9, which is over 260,000. These hyperoperations, going beyond exponentiation to tetration, and beyond, create hierarchies of growth that are staggering. They appear in mathematical logic, in the study of very large numbers, in Ramsey theory, and combinatorics, where the answers to certain problems grow faster than any tower of exponentials of fixed height. The connection to polynomials is that we use polynomial approximations to compute these functions, at least for reasonable-sized arguments. We use Taylor series to compute e raised to x, which we then use to compute factorials via Stirling's approximation, which we then use to estimate superfactorials and other hyperoperations. Polynomials have a computational foundation. Everything else is built on top of them. Even when we define transcendental functions, functions that aren't solutions to polynomial equations, we compute them using polynomials. The sine and cosine functions are defined by their Taylor series, which are polynomials with infinitely many terms. The logarithm is defined by an integral, but we compute it using polynomial approximations. The inverse tangent, the hyperbolic functions, the Bessel functions, all are ultimately approximated by polynomials when we need numerical values. This is why polynomials are the secret to mathematics. Not because everything is a polynomial, but because polynomials are how we think about everything else. They're the ladder we climb to reach higher functions. They're the scaffolding we build to support the structure of analysis. And when we study something like e raised to e, we're studying what happens when we climb very high on that ladder, when we use the scaffolding to build towers that reach toward infinity. Let's consider the aesthetics of this. Enter in a realm of whispered shadows dancing through amber light. There's a beauty in the simplicity of polynomials, and how much they can express with so little. A cubic polynomial, just 4 coefficients, can have local maxima and minima, inflection points, asymptotic behavior, richness of structure. There's a beauty in the universality of the exponential function, and how it appears in context after context. Always the solution to die over dx equals y, always the generator of growth and decay. And there's a beauty in the extremity of iterated exponentiation, and how quickly it transcends human scale, how it points to infinities beyond our everyday comprehension. Mathematics has this dual character. It's precise, rigorous, built on logic and proof. But it's also aesthetic, driven by beauty, by elegance, by the search for simple descriptions of complex phenomena. The fact that e raised to I times pi equals -1 is not just a true statement, it's a beautiful one, connecting seemingly unrelated constants in a surprising way. The fact that the sum of 1 over n squared equals pi squared over 6 is beautiful, connecting a discrete sum to a geometric constant. Similarly, The fact that polynomials can approximate any continuous function is beautiful. It says that despite infinite variety, there's underlying unity. The continuous is built from the discrete, the transcendental from the algebraic. When we compute e raised to e, we're participating in this beauty. We're taking simple rules, applying them carefully, discovering what emerges. We're explorers in a landscape of numbers, finding unexpected vistas, connections, patterns. The journey through this landscape is part of what makes mathematics compelling. Not just the destinations, the theorems and formulas, but the paths we take to reach them, the insights along the way, the moments of understanding when pieces fit together. So as we've explored polynomials and exponentials, and their iterations tonight, we've been on such a journey. We started with simple sums of powers, with coefficients and terms. We built up to Taylor series, to the representation of e raised to x as an infinite polynomial. We composed the exponential function with itself, creating towers of e's, discovering super exponential growth. We saw how differentiation and integration behave for these functions, how series nest inside series, how complexity builds. We connected to applications in science and computing, to pure mathematics and complex analysis and number theory, to philosophy about the nature of mathematical language. And underlying it all were polynomials, the simple fundamental objects, proving once again that they're not just a topic in algebra, but the foundation of all continuous mathematics. And this dark, starry, glossy matte essence, in the space of velvet midnight wrapped in silver threads, we can rest with these ideas. Let them settle, let the patterns reveal their deeper structure in the quiet. The mathematics continues, infinitely deep, infinitely rich. Each answer raises new questions. Each solution opens new problems. The Tower of E's grows without bound, but so does our understanding, our appreciation, our sense of wonder, at the structures hidden in numbers and functions. This is the gift of mathematics. Not certainty or finality, but endless exploration, endless discovery, endless beauty in the relationships between simple concepts. Polynomials are the secret, because they're the key that unlocks everything else, the foundation that supports the entire edifice. That e raised to e is a signpost pointing toward infinity, showing us how far those foundations can take us, how much can be built from how little, how the simple becomes complex, how the finite gestures toward the infinite. In molten gold dripping through prismatic silence, the equations shimmer and flow, each term a droplet of meaning, each series a stream of understanding. We follow these flows where they lead, trusting in the coherence of mathematics, and its ability to surprise and illuminate. The night is deep, the mathematics deeper still, and we've only begun to explore what lies beneath these surfaces, what connections remain to be found, what patterns wait to be discovered in the interplay of polynomials and exponentials, in the iteration of simple operations, in the endless unfolding of mathematical truth. Consider a function that curves through space, tracing a path we want to understand. We built part 1 around the idea that polynomials let us approximate this path, term by term, each addition refining our picture. Now we push deeper into what this means, into territories where polynomials stop being simple tools and become windows into structure itself. Start with differentiation again, but think of it differently this time. When you differentiate a polynomial, you're asking how it changes. The derivative of x cubed is 3x squared. The derivative of that is 6x. Then 6, then 0. Each differentiation peels away a layer, simplifies the expression, until nothing remains. This dying away of derivatives is what makes polynomials tractable. They're finite in their complexity. No matter how high the degree, enough differentiations reduce them to 0. This is unlike exponentials, unlike trigonometric functions, unlike most of the functions we care about. Those persist under differentiation, transforming but never vanishing. Yet polynomials can approximate those persistent functions. The Taylor series for sine of x starts with x minus x cubed over 6 plus x to the 5th over 120. Each term is polynomial. The infinite sum is not polynomial, but each partial sum is. We approximate the persistent with the dying, the eternal with the finite. This paradox sits at the heart of analysis. We understand the complex by building it from the simple. We reach toward infinity with finite steps. The limit process, passing from finite to infinite, is where magic happens, where discrete becomes continuous, where polynomials become everything else. Think about what polynomials really represent. They're maps from numbers to numbers. But more than that, they're the simplest such maps we can write down. To evaluate 5 plus 3x plus 2x squared at x equals 4, you compute 4 times 4 equals 16, times 2 equals 32, then 4 times 3 equals 12, then add 5. Pure arithmetic. Multiplication and addition, the operations children learn first. Compare this to evaluating sine of 4. You need infinite operations, unless you're willing to approximate, and your approximation will be a polynomial. You'll compute 4 minus 64 over 6 plus 1007. 24 over 120, stopping when further terms are negligible. So polynomials are not just simple, they're computationally fundamental. They're how we actually calculate anything. When a computer evaluates e raised to x, it's summing polynomial terms. When it computes logarithms, it's using polynomial approximations. The transcendental functions exist as limits, as ideals, but in practice we always work with polynomials. Now consider interpolation, the idea that if you give me n points, I can find a polynomial of degree n-1 that passes through all of them. Say you give me 3 points, 2, 5 and 3, 8 and 5, 14. I can find a quadratic, the polynomial of degree 2, that hits all 3 points exactly. The formula involves taking each point, building a polynomial that's 0 at the other points, and 1 at this point, multiplying by the desired value, and summing. For 3 points, this gives you 3 quadratic terms that sum to the unique quadratic through those points. This is the Lagrange interpolation formula. It proves that polynomials are universal for finite data. Any collection of points, as long as the x values are distinct, determines a unique polynomial of appropriate degree. Give me 100 points, I'll give you a polynomial of degree 99 that hits them all. This seems powerful, and it is. But there's a catch. The polynomial that interpolates many points can oscillate wildly between them. It might hit your data exactly, but behave absurdly in between. This is this phenomenon, named for a mathematician who showed that interpolating certain functions at equally spaced points gets polynomial approximations that diverge, rather than converge, as you add more points. The solution is to use different points, not equally spaced, but clustered near the endpoints. Chebyshev points, based on cosines of equally spaced angles, minimize the maximum error in polynomial interpolation. They transform a potentially divergent process into a convergent one. So even within the world of polynomials, subtlety matters. How you approximate, which points you choose, which basis you use, all affect whether your approximation succeeds or fails. Let's return to exponentials through a different lens. The function e raised to x has the property that the derivative equals the function. This makes it the eigenfunction of the derivative operator. Operators in mathematics are transformations that take functions to functions. The derivative is such an operator. An eigenfunction is a function that the operator transforms into a multiple of itself. For the derivative operator, e raised to x is an eigenfunction with eigenvalue 1. The derivative of e raised to x equals 1 times e raised to x. More generally, e raised to lambda x is an eigenfunction with eigenvalue lambda. The derivative gives you lambda times e raised to lambda x. This is why exponentials solve linear differential equations with constant coefficients. The equation d squared y over dx squared minus 3 di over dx plus 2y equals 0 becomes, when you substitute y equals e raised to lambda x, an equation for lambda. You get lambda squared minus 3 lambda plus 2 equals 0, which factors as lambda minus 1 times lambda minus 2 equals 0. So lambda equals 1, or lambda equals 2, meaning the solutions are e raised to x and e raised to 2x. Any linear combination of these is also a solution. The general solution is c1 times e raised to x plus c2 times e raised to x, plus c1 and c2 are constants determined by initial conditions. This transformation of a differential equation into an algebraic equation, this reduction of calculus to algebra, is possible because exponentials are eigenfunctions. They turn differentiation into multiplication, which is much easier to handle. Polynomials, by contrast, are not eigenfunctions of the derivative. Differentiating changes their degree, reduces their complexity. The polynomials are eigenfunctions of other operators. The shift operator, which takes f of x to f of x plus 1, has eigenfunctions that are exponentials in disguise. The operator that multiplies by x, and then differentiates, has eigenfunctions related to power functions. The interplay between operators and their eigenfunctions is a central theme in mathematics. In quantum mechanics, physical observables correspond to operators, and measurable values correspond to eigenvalues. The wave function is often an eigenfunction of the Hamiltonian operator, giving the energy of the state. In Fourier analysis, Sines and cosines are eigenfunctions of the second derivative operator. Differentiating sine of x twice gives negative sine of x. Differentiating cosine of x twice gives negative cosine of x. The eigenvalue is -1 in both cases. This is why Fourier series work for solving partial differential equations, like the He equation or wave equation. You expand the solution as a sum of sines and cosines, which are eigenfunctions, turning the PDE into infinitely many ODEs, one for each frequency. Polynomials fit into this story as building blocks for eigenfunctions. Hermite polynomials, multiplied by Gaussians, are eigenfunctions of the quantum harmonic oscillator. Legendre polynomials appear in solutions to Laplace's equation in spherical coordinates. Laguerre polynomials appear in the quantum mechanics of a hydrogen atom. These special polynomials, orthogonal polynomials, satisfy differential equations and orthogonality relations. They're the polynomial analogues of sines and cosines, forming bases for function spaces, allowing us to expand complicated functions as sums of simple, well-understood pieces. When we study e raised to x, we're looking at a function that's not an eigenfunction of any simple operator. It's a composition, a nesting, something more complex than the basic building blocks. To analyze it, we decompose that into polynomials via Taylor series, bringing it back to familiar territory. This is a general strategy in mathematics. When faced with something complex, decompose it into simple pieces. Understand the pieces, understand how they combine, reconstruct the whole. Polynomials are often those simple pieces. Consider now the question of roots. A polynomial of degree n has exactly n roots in the complex numbers, counting multiplicity. This is the fundamental theorem of algebra, proved by Gauss, though the name is somewhat misleading since the proof requires analysis, not just algebra. The roots might be real or complex. They might be distinct or repeated, but there are always exactly n of them. This is a deep and beautiful fact. Polynomials over the complex numbers are completely determined by their roots, up to a constant factor. If you know the roots are r1, r2, up to rn, the polynomial must be a constant times the product of x minus r1 times x minus r2 times time times x minus rn. Expanding this product gives you the polynomial in standard form, with its coefficients expressed in terms of the roots. The coefficients are symmetric functions of the roots. The coefficient of x to the n minus 1 is -1 times the sum of the roots. The constant term is -1 to the n times the product of the roots. The coefficient of x to the n minus 2 is plus or minus the sum of products of roots taken 2 at a time. These are the elementary symmetric polynomials in the roots. They connect the coefficients, which we can see, to the roots, which we often want to find. Solving a polynomial equation means finding the roots, given the coefficients, inverting these symmetric functions. For quadratic equations degree 2, there's a formula. The roots are negative, b plus or minus the square root of b squared minus 4ac, all divided by 2a, where a is the leading coefficient, b is the coefficient of x, and c is the constant term. For cube equations, degree 3, there's a formula, though it's more complex. It involves cube roots and can produce 3 real roots expressed in terms of complex numbers, which is strange but unavoidable. For quartic equations, degree 4, there's an even more complex formula, but for degree 5 and higher, there is no formula in general. This is the Abel-Ruffini theorem, one of the great negative results in mathematics. You cannot express the roots of a general quintic polynomial using only arithmetic operations and radicals, taking roots. This doesn't mean quintic equations are unsolvable. It means they're not solvable by the methods that work for lower degrees. Numerical methods can find roots to any desired accuracy. Special quintics, those with particular symmetries or structures, might be solvable exactly. But in general, the roots exist as transcendental functions of the coefficients, not expressible in closed form. This is a limitation of polynomials, or perhaps a richness. Even these simple objects have aspects we cannot fully tame. The roots are there, guaranteed to exist, but beyond our algebraic reach, except in special cases. For exponentials like e raised to x, the question of roots is different. When does e raised to x equal 0? Never for real x. The exponential function is always positive. Even for complex x, e raised to z is never 0. The exponential function is a non-vanishing entire function, analytic everywhere, and 0 nowhere. The equation e raised to x equals 1 has solutions. If e raised to x equals 0, then e raised to x equals 0, then e raised to x equals 0. However, e raised to x never equals 0. However, e raised to x equals 2 pi I times n. For any integer n, gives e raised to x equals e raised to 2 pi I times n equals 1. So the solutions are x equals natural log of 2 pi I times n equals natural log of 2 pi I times n plus I times pi over 2. These are complex solutions spaced periodically along a vertical line in the complex plane. This periodicity reflects the periodic nature of the exponential function in the complex plane. It's periodic in the imaginary direction with period 2 pi I. This is Euler's formula, e raised to I times theta equals cosine theta plus I times sine theta, which repeats when theta increases by 2 pi. The nesting in e raised to x compounds this periodicity. If the inner exponential changes by 2 pi how, the outer exponential cycles back to the same value. This creates a kind of vertical periodicity in the behavior of the function. Visualizing this requires thinking in 4 dimensions, 2 for the input complex plane, and 2 for the output complex plane. Or we can visualize magnitude and phase separately. The magnitude of e raised to x grows extremely rapidly for real x, but oscillates in complex patterns for imaginary x. The phase winds around in intricate ways. The function has essential singularities at infinity, in various directions in the complex plane. Near these singularities the function exhibits wild behavior, taking on every complex value infinitely, often in any neighborhood. This is Picard's theorem. An entire function that's not a polynomial takes on every complex value, with at most one exception, infinitely often. For e raised to x, the exception is 0, which is never achieved. Every other complex number is a value of the function infinitely many times. So even though the function seems simple when restricted to real numbers, just a rapidly growing causative function, its full complex behavior is incredibly rich. This is common. Complex analysis reveals depths hidden when we restrict to real numbers. Let's think about series convergence more carefully. When we write e raised to x equals the sum from n equals 0 to infinity of x to the n over n factorial, we're claiming this infinite sum equals the function value for every x. Does it mean for an infinite sum to equal something? It means the sequence of partial sums converges. The partial sum Sn equals the sum from k equals 0 to n of x to the k over k factorial. As n goes to infinity, Sn approaches e raised to x. For any desired accuracy, epsilon, there exists an n, such that for all n greater than n, the absolute value of Sn minus e raised to x is less than epsilon. This is the definition of convergence. It's not that we ever actually sum infinitely many terms. We sum finitely many, getting closer and closer to the true value, and we can get as close as we want by taking enough terms. For the exponential function, this convergence is rapid. The terms x to the n over n factorial decrease quickly once n is larger than the absolute value of x. Factorials grow faster than exponentials, so eventually each term is smaller than the previous one, and the sum of the tail, all terms from some point onward, can be made arbitrarily small. This rapid convergence is why the exponential function is so computationally accessible. A few dozen terms usually suffice for double precision accuracy, even for moderately large x. For e raised to x, the Taylor series coefficients grow much faster. The nth coefficient involves sums over partitions and combinatorial structures. Computing it exactly for large n is difficult. But for numerical evaluation at a specific x, we can still compute partial sums and get good approximations. The key insight is that even if we don't have a simple formula for the coefficients, the series still converges, and we can compute as many terms as we need for our purposes. This is the difference between symbolic and numerical mathematics. Symbolically, e raised to x is a simple expression. Numerically it requires work to evaluate, but that work is systematic and well understood. Now consider the integral of e raised to x, which is just e raised to x plus c. Integration is in some sense the point inverse of differentiation. If the derivative of f equals g, then the integral of g equals f plus a constant. For the exponential function, being its own derivative, means it's also its own integral, up to that constant. But the integral of e raised to x is not expressible in elementary functions. We cannot write it as a finite combination of polynomials, exponentials, logarithms, trigonometric functions. It requires either a new special function defined specifically for this purpose, or an expression as an infinite series. This is typical. Most functions do not have elementary antiderivatives. Integration is harder than differentiation. We can differentiate anything we can write down, using the chain rule, product rule, quotient rule. But we can integrate only a small class of functions explicitly. This seems unfair. Why should going forward, differentiating, be easy, while going backward, integrating, be hard? The reason is that differentiation is local. To find the derivative at a point, we only need information near that point. Integration is global. To find the integral over an interval, we need information across the entire interval. Differentiation simplifies. Integration complicates. When we differentiate a product, we get a sum. When we integrate a product, we might need integration by parts, substitution, partial fractions, tricks and techniques that don't always work. Yet integration is fundamental to mathematics. Areas under curves, solutions to differential equations, probabilities, expectations, all involve integrals. We need ways to handle them even when we can't solve them explicitly. Numerical integration, approximating integrals with sums, is one approach. The trapezoidal rule, Simpson's rule, Gaussian quadrature, all approximate the integral of a function over an interval by evaluating the function at specific points and weighting appropriately. These methods rely on polynomial interpolation. We approximate the function with a polynomial over small intervals, integrate the polynomial exactly, and sum the results. Since polynomials are easy to integrate, this reduces the hard problem to many easy problems. Series methods are another approach. If we have a series representation of a function, we can integrate term by term, getting a series representation of the antiderivative. For e raised to x, integrating the series for e raised to x term by term gives the same series back, confirming that the integral is e raised to x plus c. For e raised to x, we could expand as a Taylor series, integrate term by term, and get a series for the antiderivative. Each term x to the n over n factorial integrates to x to the n plus 1 over n times n plus 1 factorial. The antiderivative is the sum of these terms, plus a constant. This series representation is valid and exact. It's just not a closed-form expression. We've traded one infinite process, integration, for another, summation. For practical computation, this might be fine. For symbolic manipulation, it's less satisfying. The question of which functions have elementary antiderivatives is answered by differential Galois theory, an analog of classical Galois theory, for differential equations instead of polynomial equations. It provides criteria for determining whether an antiderivative can be expressed using elementary functions. For many functions, including e raised to x, the answer is no. The antiderivative exists, is unique up to a constant, is perfectly well defined, but cannot be written in closed form, using the functions we've agreed to call elementary. This forces us to expand our vocabulary. We define new functions as integrals of known functions. The error function, the logarithmic integral, the exponential integral, all are defined this way. They become new building blocks, new tools in our toolkit. In a sense, the exponential function itself is defined as the solution to di over dx equals y with y of 0 equals 1. We could solve this by separation of variables, getting di over y equals dx, integrating to get natural log of y equals x plus c, exponentiating to get y equals e raised to x plus c, which with the initial condition gives y equals e raised to x. But this assumes we know what the logarithm is, what exponentiation means. At a foundational level, we might define the natural logarithm as the integral from 1 to x of 1 over t dt. Then e is the number such that the integral from 1 to e of 1 over t dt equals 1. Then e raised to x is defined as the inverse function of the logarithm. These circular definitions can be made rigorous, that they illustrate that our defic functions are interconnected, each definable in terms of others, the whole structure resting on a foundation of limits and continuity. Polynomials escape this circularity. They're defined purely algebraically, no limits, no integrals, no transcendental operations, just multiplication and addition. This is why they're foundational in a different sense. They don't require the machinery of analysis to define, only the basic arithmetic of numbers. Yet to fully understand polynomials, to prove the fundamental theorem of algebra, for instance, we need complex analysis. We need topology, the compactness of the Riemann sphere, the intermediate value theorem, Liouville's theorem. So even polynomials, simple as they seem, are deeply connected to analysis. This interconnectedness is part of the beauty of mathematics. Every part connects to every other part. Polynomials lead to complex numbers, lead to analytic functions, lead to special functions. lead back to polynomials. The circle is not vicious, but virtuous, each perspective enriching the others. Consider now the rate of growth of factorials. We know n factorial equals 1 times 2 times 3 times ... times n. This product grows rapidly. 10 factorial is over 3 million. 20 factorial is over 2 quintillion. 30 factorial is over 200 undecillion. Stirling's approximation gives us a formula for n factorial when n is large. It says n factorial is approximately the square root of 2 pi times n over e, all raised to the n. More precisely, the ratio of n factorial to this approximation approaches 1 as n goes to infinity. This approximation is remarkably accurate, even for small m. For 10 factorial, it gives about 3,600,000 compared to the true value of about 3,628,000. The error is less than 1%. Why does this approximation work? It comes from applying advanced techniques in analysis, specifically the method of steepest descent, to the integral representation of the gamma function. The gamma function is defined for positive x as the integral from 0 to infinity of t raised to x minus 1 times e raised to negative t dt. For positive integers n, gamma of m equals n minus 1 factorial. The integral representation extends factorial to all complex numbers, except negative integers. Stirling's approximation follows from analyzing this integral for large n. The formula involves e in an essential way. The n over e raised to the n term comes from the exponential growth of n to the n being tempered by e to the negative n, balancing power against exponential. When we compute terms in the Taylor series for e raised to x, we're dividing powers of e raised to x by factorials. For e raised to e itself, about 15.15, the terms e raised to n decrease slowly, while n factorial increases rapidly. The ratio e raised to n, then raise of n factorial, determines the magnitude of each term in the series. For small m, e raised to n is larger than n factorial. E raised to e is about 15, larger than 1 factorial. E raised to e squared is about 227, larger than 2 factorial, which is 2. E raised to e cubed is about the 33,000, still larger than 3 factorial, which is 6. Around n equals 7 or 8, the factorial starts to overtake. Factorial is about 40,000, while e raised to 8 is about 63,000. The ratio is still greater than 1. By n equals 10, 10 factorial is about 3.6 million, while e raised to 10 is about 92,000. Now the ratio is less than 1. From this point on, the factorial dominates, the terms decrease, and the series converges. The sum of all these terms gives us e raised to e, approximately 15.15. Understanding this behavior, why the terms initially grow then shrink, why the series converges despite the rapid growth of e raised to x, is key to understanding exponential functions and their compositions. Now think about continued fractions, another way to represent numbers. A continued fraction expresses a number as an integer, plus 1 over another continued fraction. For example, the golden ratio equals 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1. Finite continued fractions represent rationals. Infinite continued fractions can represent irrationals. The continued fraction expanses of a number is in some sense its most efficient rational approximation at each stage. The exponential e has a beautiful continued fraction. It equals 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 4 plus 1 over 1 plus 1 over 4. Slash n over 6, with the pattern 2, 1, 2, 1, 2, 4, 1, 1, 6 appearing. The integers 1, 2, 1, 1, 4, 1, 1, 6 appearing. The integers 1, 2, 1, 4, 4, 1, 6, 1 second, 8 follow a pattern. Every third term is 2 times an increasing sequence. This pattern relates to the representation of e as a sum of reciprocals of factorials. Continued fractions provide a different lens on numbers. They emphasize rational approximations, the arithmetic structure, patterns in the digits. For algebraic numbers, solutions to polynomial equations, the continued fraction is eventually periodic. For transcendental numbers like e and pi, the patterns are more subtle. E raised to e, being approximately 15.15, has its own continued fraction. It starts 15 plus 1 over 6, plus 1 over 1 plus 1 over 2, continuing with no obvious pattern. The terms reflect the arithmetic properties of e raised to e, which is transcendental like E itself. Power towers of E's, E raised to E, raised to E and beyond, have continued fraction expansions that become increasingly complex. The connection between the exponential representation and the continued fraction representation is deep, but not fully understood for these higher towers. Continued fractions connect to Diophantine approximation, the study of how well real numbers can be approximated by rationals. A number is badly approximable if its continued fraction coefficients grow slowly. A number is well approximable if some coefficients are very large. The golden ratio, with all coefficients equal to 1, is the worst possible case for approximation. It's the hardest number to approximate rationally in a certain precise sense. This is related to its appearance in the Fibonacci sequence, where each term is the sum of the previous two, giving ratios that approximate the golden ratio. E raised to E raised to E, being such a large number, is well approximated by integers or simple rationals just by rounding. That its fine structure, the decimal expansion beyond the first few digits, has its own complexity. The decimal expansion of E raised to E starts 15.15426, continuing with no repeating pattern since the number is transcendental. Computing more digits requires either high precision evaluation of the exponential function or high precision summation of the Taylor series. Each digit we compute gives us more information about the number, but in some sense we never fully capture it. The number has infinitely many digits. We can compute as many as we want, but never all. This is the nature of real numbers. Their limits are sequences of rationals, approximations that converge, but never quite arrive. Polynomials, by contrast, are fully determined by finitely many coefficients. A polynomial of degree n is specified by n plus 1 numbers, the coefficients. We can write it down completely, explicitly, finitely. This is part of their simplicity and their power. Transcendental functions like e raised to x require infinite data to specify exactly, either as infinite series or as solutions to differential equations, or as limits. We could approximate them with polynomials, but the full function escapes finite description. Yet in practice, finite approximations suffice. We never need infinite precision. 15 digits of e raised to e is more than enough for any physical application. The diameter of the observable universe is only about 10 to the 60 times the Planck length. 15 digits of e raised to e exceeds any precision relevant to physics. So the distinction between finite and infinite, between polynomial and transcendental, matters philosophically and mathematically, but not always practically. We live in a finite world, computationally and physically, and polynomials suffice for everything we actually do. This is why numerical methods work. We replace infinite processes with finite approximations, and the approximations are good enough. Error bounds tell us how good, how many terms we need, how much we can trust the result. Consider Monte Carlo methods, which use randomness to approximate integrals, or solve problems. You generate random points, evaluate the function, average the results. By the law of large numbers, the average converges to the integral, to the true value, as the number of points increases. This is a different kind of approximation, not polynomial, not series-based, but statistical. Yet it works, often efficiently, for problems where other methods struggle. In high dimensions, where the curse of dimensionality makes grid-based methods infeasible, Monte Carlo shines. Random sampling doesn't care about dimension. A million random points is a million random points whether the space is 3-dimensional or 3,000-dimensional. But for our purposes, thinking about e raised to e, one-dimensional functions, polynomials and series, are the natural tools. We sum terms, truncate when accuracy suffices, and get numerical values we can work with. The psychology of large numbers is worth considering. We understand small numbers intuitively. 5 apples, 10 people, $100. But a million, the billion? These are just words, labels for quantities, beyond direct perception. E raised to e is about 15. That's still graspable. E raised to e is about 3 million. That's big, but not unimaginable. A city might have 1 million people. 3 million is 3 such cities. E raised to e, raised to e, raised to e is approximately 10 to the 6 millionth power. This number is so large it defies comprehension. It has over 6 million digits. If you wrote a digit per second, it would take months to write. If you used 1 atom per digit, you'd need more atoms than exist in observable galaxies. At this scale, numbers cease to have direct meaning. They become abstract tokens, symbols we manipulate, but not quantities we understand viscerally. This is where mathematics departs from experience, where we need formalism to guide us, because intuition fails. Yet the formalism works. The rules of arithmetic, the properties of exponentials, the convergence of series, all apply just as well to e raised, to e raised, to e raised, to e is to 5, plus 3. The mathematics doesn't care about our psychological limitations. This is liberating and humbling. Liberating because we can reason about things far beyond experience. Humbling because we realize how limited our intuition is, how much we depend on tools and structures to extend our reach. Polynomials are one such tool. They let us compute, approximate, reason about functions we cannot directly grasp. They're the cognitive prosthesis that lets us do mathematics beyond mental arithmetic. In education, polynomials are often taught as just another topic. Quadratic formula, factoring, graphing parabolas. But there's so much more. They're the foundation of continuous mathematics, the bridge from algebra to analysis, the key to understanding how we compute anything. Recognizing this changes how we might teach them, not as isolated techniques, but as part of a larger story about approximation, about representation, about how we make the complex tractable. The story we've been telling, from simple sums of powers to Taylor series to power towers of ease, illustrates this. Each step builds on the previous. Each idea connects to others, the whole forming a web of understanding. And at the center of that web are polynomials, simple, foundational, indispensable. They're the reason we can do calculus. Without polynomials, we could define derivatives and integrals abstractly, but we couldn't compute them. We couldn't solve equations, model phenomena, make predictions. With polynomials, all of this becomes possible. We approximate smooth functions, integrate term by term, solve differential equations, fit data, compress information, encode signals. The applications are endless, because polynomials are universal. So when we computed e raised to e, we were not just calculating a number, we were demonstrating the power of polynomial approximation, the universality of Taylor series, the way simple sums of powers can reach any function, any value, given enough terms. And we were exploring the edges of this universality. E raised to e grows so fast it challenges our methods. The Taylor series still works, but we need more terms, higher precision, careful error analysis. We're pushing polynomials to their limits, seeing where the approximation struggles and where it succeeds. This exploration is valuable in itself. Mathematics grows by finding limits, boundaries, edges. We push methods until they break, then develop new methods, stronger tools, deeper theories. Polynomials lead to series, lead to complex analysis, lead to special functions, each stage expanding what we can express and compute. The journey never ends. There are always deeper questions, harder problems, richer structures to discover. E raised to e is one small station on an infinite line, interesting for what it teaches us, for the methods we develop to understand it, for the connections it reveals to other areas of mathematics. In the quietness of this exploration, patterns emerge. We see symmetry in the coefficients of series, order in the chaos of rapid growth, beauty in the relationships between seemingly unrelated concepts. This is why mathematicians work. Not for applications, though those matter, but for the joy of discovery, the satisfaction of understanding, the aesthetic pleasure of elegant structures. Polynomials embody this elegance. They're simple enough to grasp completely, yet rich enough to support the entire edifice of modern mathematics. They're elementary, in the best sense, fundamental elements from which everything else is built. And exponentials, particularly the base e, are their natural partners. Where polynomials are discrete, finite sums of powers, exponentials are continuous growth, infinite in their reach. Together, they span the space between algebra and analysis, between the countable and the continuous. Our exploration of e raised to e, has been an exploration of this partnership. How polynomials approximate exponentials. How compositions of exponentials create super-exponential growth. How series converge despite the rapid increase. How we compute with infinite sums that we truncate to finite ones. And through it all, the mathematics remains coherent, consistent, beautiful. The definitions hold, the theorems apply, the calculations work. We can trust the process because the foundations are solid, the logic sound, the structure carefully built over centuries of mathematical thought. This trust is what allows us to work with confidence in realms far beyond direct experience. We know e raised to e is unimaginably large. But we also know we can compute it, bound it, relate it to other quantities, understand its properties. The mathematics gives us purchase on the infinite. the tools to grapple with the abstract. And at the heart of those tools are polynomials, those simple sums of powers, proving once more that they're not just a topic in algebra, but the secret foundation of all continuous mathematics, the key that unlocks everything else, the reason we can do what we do. This is the gift they offer, and understanding it deepens our appreciation not just of polynomials but of mathematics itself, of how simple rules generate infinite complexity, of how finite minds can grasp truths beyond imagination, of how beauty and utility intertwine in the structures we discover and create. Looking at the landscape we've mapped so far, where polynomials serve as our foundation and exponentials reveal depths, we can only glimpse through infinite processes. We arrive now at questions of structure itself. What happens when we step back from individual functions and ask about the spaces they inhabit, the transformations that connect them, the patterns that emerge when we view mathematics not as isolated objects, but as vast interconnected territories? Consider the real number line. Every point represents a number, but more than that, every number represents a potential input to any function we might imagine. The line extends infinitely in both directions, dense with rational numbers, yet mostly filled with irrationals, those numbers that cannot be expressed as fractions, whose decimal expansions never repeat. Between any two real numbers, no matter how close, infinitely many other real numbers nestle. This density means the real line has no gaps in a certain sense. Yet it's also riddled with structure. The rationals are countable, meaning we could theoretically list them all, while the reals are uncountable, a larger infinity. Most real numbers are transcendental, not roots of any polynomial equation with rational coefficients. The exponential function e raised to x maps this real line to the positive half of itself. Every real input produces a positive real output. 0 maps to 1. Positive inputs map to numbers greater than 1. Negative inputs map to numbers between 0 and 1. The function is continuous, smooth, always increasing, never bending back on itself. This mapping has interesting properties. It's injective, meaning different inputs always give different outputs. It's surjective onto the positive reals, meaning every positive number is the exponential of some real number. Together these properties make e raised to x a bijection from all reals to positive reals, a perfect one-to-one correspondence. The inverse function, the natural logarithm, maps positive reals back to all reals. The composition of a function with its inverse gives the identity e raised to the natural log of x equals x for positive x. The natural log of e raised to x equals x for all real x. These identities express the fundamental relationship between exponential and logarithm, two sides of the same coin. Now think about what happens when we compose exponentials with themselves. The function e raised to x is no longer a simple bijection. It maps reals to positive reals, but not surjectively. The smallest value it achieves, when x approaches negative infinity, is 0 as a limit, but never actually 0. When x equals negative infinity in a limiting sense, e raised to x approaches 0, so e raised to x approaches e raised to 0 equals 1. Actually, let me reconsider. As x decreases toward negative infinity, e raised to x decreases toward 0. So e raised to x decreases toward e raised to 0 equals 1. But it approaches from above. The function never actually reaches 1 for any finite x. When x equals 0, e raised to x equals 1. So e raised to x equals 1. So e raised to x, and then x increases. The function grows without bound, faster than any exponential of x itself. This super-exponential growth is characteristic of iterated exponentials. Each nesting multiplies the growth rate. E raised to x grows exponentially. E raised to x grows exponentially in the exponent, which means it grows faster than any polynomial power of e raised to x. E raised to x would grow faster still, and so on. These towers of exponentials appear in combinatorics, in the sizes of certain finite structures, in the complexity of algorithms. They represent growth so rapid it's almost incomprehensible. The difference between e raised to 100 and e raised to 100 is unimaginably vast, far larger than the difference between 100 and raised to 100. Yet we can still analyze these functions using the tools we've developed. Series expansions work locally. Near any point where we want to approximate, differential equations might capture their behavior implicitly, even if we can't solve them explicitly. Numerical methods let us compute values to any desired precision. The interplay between symbolic and numeric understanding runs throughout mathematics. Symbolically, we manipulate expressions, proving theorems, deriving identities, understanding relationships. Numerically, we compute specific values, solve equations approximately, visualize behavior. Neither approach alone suffices. Together they give us leverage. Returning polynomials, consider them not just as individual functions, but as elements of a vector space. The set of all polynomials of degree, at most, n forms a vector space, of dimension n plus 1. A basis for this space consists of 1, x squared, up to x to the n. Any polynomial in space can be written uniquely as a linear combination of these basis elements. Linear combinations mean we can add polynomials and multiply them by constants. Adding two polynomials adds their coefficients. Multiplying a polynomial by a constant multiplies all coefficients by that constant. These operations satisfy the axioms of a vector space. There's a zero element, addition is commutative and associative, scalar multiplication is compatible with field multiplication, and so on. This vector space structure is not just formal. It gives us tools. We can talk about dimension, about bases, about linear transformations. Differentiation is a linear transformation from the space of polynomials of degree at most n to the space of polynomials of degree at most n minus 1. It takes a vector space to another vector space respecting the linear structure. Similarly, integration is a linear transformation, though it increases degree. Multiplying by x is a linear transformation that also increases degree. These transformations can be composed, inverted when possible, studied using linear algebra. The matrix representation of a linear transformation depends on a choice of bases. In the standard basis of 1, x squared, differentiation is represented by a matrix that's mostly zeros, with the diagonal just above the main diagonal containing the values 1, 2, 3, and so on. This matrix acts on the coefficient vector, transforming a polynomial to its derivative. Understanding transformations through matrices connects calculus to linear algebra. The eigenvalues and eigenvectors of a transformation tell us about invariant directions, about how the transformation stretches or rotates, or reflects the space. For differentiation on polynomials, the only eigenvector is 0, since differentiation always reduces degree for non-zero polynomials. But if we extend our space to include all formal power series, infinite sums of the form sum of a times x to the n, then exponentials become eigenvectors. The series for e raised to lambda x is an eigenvector with eigenvalue lambda. The series for sine and cosine become eigenvectors of the second derivative, with eigenvalues -1. This extension from finite-dimensional polynomial spaces to infinite-dimensional function spaces is both natural and subtle. Many concepts from finite dimensions carry over: bases, linear combinations, transformations. But new phenomena appear. Convergence matters. Not all formal sums represent functions. Topology enters, the study of closeness and limits and continuity. In finite dimensions, all norms are equivalent. Two different ways of measuring the size of a vector give rise to the same notion of convergence. In infinite dimensions, this fails. The space of continuous functions on an interval has multiple natural norms, and they're not equivalent. Some sequences converge in one norm, but not another. The space of squared integrable functions, those whose squared magnitude integrates to a finite value, forms a Hilbert space. This is an infinite dimensional vector space, with an inner product, a way of measuring angles and lengths. The inner product of two functions, f and g, is the integral of f times the complex conjugate of g. In this space, we can talk about orthogonal functions, those whose inner product is 0. Sines and cosines of different frequencies are orthogonal in this sense. So are Legendre polynomials, Hermite polynomials, Laguerre polynomials, all the orthogonal polynomials families that appear in mathematical physics. Orthogonal functions are useful for the same reason. Orthogonal vectors are useful in finite dimensions. They provide independent directions. Expanding a function as a sum of orthogonal functions is like expressing a vector in terms of orthogonal basis vectors. The coefficients can be computed independently using inner products. Fourier series expand periodic functions as sums of sines and cosines. The coefficients are the inner products of the function with each sine or cosine. Since the sines and cosines are orthogonal, these coefficients capture independent information about the function. Together, they reconstruct the function, at least in the limit. For smooth periodic functions, Fourier series converge quickly. For functions with discontinuities, The series converge more slowly and exhibit Gibbs phenomenon, an overshoot near jumps that never quite goes away. For functions that aren't even square integrable, the series might not converge at all in the usual sense. These convergence questions are subtle and important. When we say a series equals a function, we need to specify what kind of convergence we mean. Pointwise convergence means at each point the series converges to the function value. Uniform convergence means the convergence is equally good at all points simultaneously. Convergence in mean means the integral of the squared difference goes to 0. Different notions of convergence are appropriate for different purposes. Uniform convergence preserves continuity. If a sequence of continuous functions converges uniformly, the limit is continuous. Pointwise convergence doesn't have this property. A sequence of continuous functions can converge pointwise to a discontinuous function. For Fourier series, convergence in mean is guaranteed for square integrable functions. Pointwise convergence is guaranteed at points where the function is smooth. Uniform convergence happens for continuously differentiable periodic functions. These results, the theorems of Fourier analysis, specify precisely when and how Fourier series represent functions. The exponential function, being smooth and periodic in the complex plane, with period 2 pi I, has well-behaved Fourier series when restricted to any horizontal strip. The series converge rapidly, allowing accurate approximation with few terms. But e raised to x is not periodic, even in the complex plane. It has more complicated behavior. We cannot expand it as a Fourier series in the usual sense. We need other tools, other series, other approximation methods. One approach is to use Taylor series near specific points. Near x equals 0, we've discussed the series. Near x equals 1, we could expand in powers of x minus 1, getting different coefficients, but the same function. Each Taylor series has a radius of convergence, a region where it represents the function accurately. For entire functions like e raised to x, functions analytic everywhere in the complex plane, the Taylor series around any point converges everywhere. But the rate of convergence varies. Far from the expansion point, more terms are needed for a given accuracy. Another approach is asymptotic expansion. Instead of trying to represent the function exactly, we find a series that approximates it in a limiting regime. For e raised to x, as x goes to infinity, we can derive an asymptotic series in powers of 1 over x, or more accurately in powers of 1 over e raised to x. These asymptotic series often diverge. The terms decrease at first, but eventually grow without bound. Yet they're useful. If we truncate at the smallest term, we get an approximation that's extremely accurate, that even any convergent series might provide with comparable effort. This seems paradoxical. How can a divergent series be useful? The answer lies in understanding what the series represents. It's not claiming the infinite sum equals the function. It's claiming that for large x, the function minus the first n terms of the series is smaller than the n plus first term, in a specific technical sense. This is good enough for many purposes. We can compute the function to high accuracy using just a few terms. The fact that including more terms eventually makes things worse doesn't matter if we stop at the optimal truncation point. Asymptotics is the art of understanding behavior and limits. As x goes to infinity, as a parameter goes to 0, as a dimension increases, functions exhibit characteristic behaviors. Capturing these behaviors with simple expressions, even if those expressions are only approximations, gives insight and computational power. For e raised to x, the dominant behavior as x increases is clear. The function grows like e raised to x, which is to say it is what it is. We can't simplify it to something more elementary, but we can understand how rapidly it grows, how it compares to other functions, what happens if we perturb it slightly. Perturbation theory, the study of how solutions change when we slightly modify a problem, is central to applied mathematics. Often we can solve a simplified problem exactly, but only approximately solve the real problem. Perturbation methods let us use the simple solution as a starting point, correcting it systematically. For differential equations, perturbation methods expand the solution as a series in a small parameter. The 0th order term solves the simplified equation. The 1st order term corrects for the perturbation. Higher order terms refine the correction. If the series converges, we get the exact solution. If it diverges, we still get useful asymptotic information. The exponential function appears constantly in perturbation theory because it solves linear constant coefficient equations exactly. We perturb around exponential solutions, finding corrections that account for nonlinearity, variable coefficients, and homogeneities. Nested exponentials like e raised to x appear in nonlinear problems where the perturbation itself involves exponentials. Certain models of population growth, the growth rate depends exponentially on the population, lead to such equations. The solutions exhibit rapid transitions, sharp thresholds, behaviors that linear models cannot capture. These nonlinear phenomena are among the richest areas of modern mathematics. Chaos theory, bifurcation theory, dynamical systems, all study what happens when linearity breaks down. Small changes in initial conditions can lead to large changes in outcomes. Systems can transition suddenly from one behavior to another. Simple equations can produce incredibly complex dynamics. The logistic map, defined by x goes to r times x times 1 minus x, is a simple quadratic but exhibits chaos for certain values of r. Iterating the map, feeding the output back as the next input, produces sequences that appear random despite being deterministic. This sensitivity to initial conditions, this unpredictability from simple rules, is characteristic of chaos. Exponential maps, x goes to r times e raised to x, or variations, also exhibit chaos. The iteration of exponentials is less studied than polynomials, but no less rich. The Julia sets and Fatou sets, regions of different dynamical behavior in the complex plane, have fractal structure for exponential maps, just as they do for polynomial maps. Fractals sets with self-similar structure at all scales appear throughout mathematics. The Mandelbrot set, defined by iterating z, goes to z squared plus c, and asking whether the orbit stays bounded, is perhaps the most famous. Its boundary is fractal, infinitely detailed, never smoothing out no matter how much we zoom in. For exponential maps, similar sets exist. They're harder to compute, because exponentials grow faster than polynomials, causing numerical overflow more easily. But mathematically, they're just as well defined, just as beautiful, just as complex. Complexity here means more than just complicated. It means exhibiting structure at all scales, having dimension that's not an integer, possess statistical properties that remain consistent in their magnification. Fractals are complex in a measurable, quantifiable sense. The dimension of a fractal, the Hausdorff dimension, can be a non-integer value between the topological dimension and the dimension of the space containing it. A fractal curve in the plane might have dimension 1.5, meaning it's more than a line but less than an area. This fractional dimension reflects how much space the set occupies in a scaling sense. Computing Hausdorff dimension rigorously is difficult. Often we use box counting dimension, covering the set with boxes of size epsilon, and seeing how the number of boxes scales as epsilon decreases. If the number scales like epsilon to the negative d, then d is the dimension. For the boundary of the Mandelbrot set, the dimension is believed to be 2, the same as the plane, though this hasn't been rigorously proven. For other fractals, like the Cantor set, or Sierpinski triangle, we can compute dimensions exactly. The Cantor set has dimension natural log of 2 over natural log of 3, about 0.63. These fractal sets connect to exponentials through dynamics. The stable and unstable manifolds of hyperbolic fixed points in dynamical systems are often fractal. The base and boundaries separating different behaviors are fractal. Exponentials, with their rapid growth, create the nonlinearity needed for this complexity to emerge. Let's shift perspective again, and think about functions as objects we can manipulate, transform, combine in various ways. We've discussed composition, nesting functions inside each other. We've discussed arithmetic, adding and multiplying functions. We've discussed differentiation and integration, calculus operations that transform functions to related functions. Another operation is convolution, blending two functions together in a specific way. The convolution of f and g is defined as the integral of f of t times g of x minus t over all t. This creates a new function that smooths both inputs, capturing their combined effect. Convolution appears in probability, where the sum of independent random variables has a probability density that's the convolution of the individual densities. It appears in signal processing, where a system's output is the convolution of the input with the system's impulse response. It appears in differential equations, where convolution with the Green's function solves inhomogeneous equations. The Fourier transform converts convolution to pointwise multiplication. The Fourier transform of a convolution is the product of the Fourier transforms. This property makes Fourier methods powerful for solving problems involving convolution. Transform both functions, multiply, transform back. The Fourier transform itself is an integral transform, taking the function to a new function that encodes the same information in a different way. The transform of f is the integral of f of t times e raised to negative I omega t over all t, where omega is the frequency variable. This transform decomposes f into its frequency components. Each value of omega corresponds to a pure oscillation at that frequency. The transform value at omega tells us how much of that frequency is present in f. For a pure sine or cosine of frequency omega 0, the transform is concentrated at omega equals omega 0 and omega equals negative omega 0. The exponential function e raised to negative I omega t is the key to this decomposition. It's a complex exponential, combining cosine and sine via Euler's formula. Its magnitude is 1, so it doesn't amplify or attenuate. Its phase rotates at a constant rate, determined by omega. Multiplying f by this exponential, and integrating effectively picks out the component of f that oscillates at frequency omega. Components of other frequencies average to 0, due to orthogonality. Components at the same frequency reinforce. The inverse Fourier transform reconstructs f from its I transform. The formulas are symmetric, differing only in the sign of the exponent and normalization constants. The symmetry reflects a deep duality between time and frequency, position and momentum, space and wave number. In quantum mechanics, the position wave function and momentum wave function are Fourier transforms of each other. Measuring one destroys information about the other, a manifestation of the uncertainty principle. The product of position uncertainty and momentum uncertainty is bounded below by Planck's constant. This uncertainty is not due to measurement imperfection. It's fundamental, built into the mathematics of wave functions and operators. The position operator and momentum operator do not commute. Their commutator is a constant times the identity. This algebraic relation encodes the uncertainty principle. Exponentials appear here too, as eigenfunctions of the momentum operator. The wave function e raised to ikx is an eigenfunction, with eigenvalue k. It represents a particle with definite momentum. Completely uncertain position, since the magnitude of the wave function is constant everywhere. Conversely, a delta function, infinitely narrow and infinitely tall, represents a particle with definite position, but completely uncertain momentum. Its Fourier transform is constant, containing all frequencies equally. Real particles are described by wave packets, localized in both position and momentum, to the extent allowed by uncertainty. A Gaussian wave packet minimizes the uncertainty product, saturating the bound. Its position and momentum distributions are both Gaussian, related by Fourier transform. The time evolution of a wave packet is governed by the Schrödinger equation, a differential equation with the Hamiltonian operator. For a free particle, the Hamiltonian is the kinetic energy, proportional to the square of the momentum operator, which is minus the second spatial derivative. Solving the Schrödinger equation for a free particle is straightforward in momentum space. Each momentum component evolves independently, accumulating a phase proportional to the energy. In position space, this corresponds to the wave packet spreading out over time, while maintaining its center of mass motion. For a particle in a potential, the Hamiltonian includes both kinetic and potential energy. The eigenfunctions are no longer simple exponentials. For the harmonic oscillator, they're Hermite polynomials times Gaussians. For the hydrogen atom, they're products of spherical harmonics and Laguerre polynomials times exponentials. These special functions, solutions to differential equations with physical significance, form orthogonal bases for the relevant function spaces. We expand arbitrary wave functions in these bases, reducing the dynamics to evolution of coefficients. The connection between differential equations and orthogonal polynomials is deep. The Hermann equation, Legendre equation, Laguerre equation, all have polynomial solutions for specific parameter values. These polynomials satisfy orthogonality relations with respect to wave functions, Gaussians for Hermite, constant for Legendre, exponentials for Laguerre. The wave functions make the differential equations self-adjoint, ensuring real eigenvalues and orthogonal eigenfunctions. Self-adjoint operators are the analog of symmetric matrices, having nice spectral properties, decomposing spaces into orthogonal eigenspaces. For the function e raised to x, there's no simple differential equation it satisfies. It's not an eigenfunction of any standard operator. It's not associated with an orthogonal polynomial family. It exists as a composition, built from simpler pieces, but not reducible to them in any elementary way. This irreducibility is common. Most functions are not special. They don't satisfy simple equations, don't have simple transforms, don't decompose nicely. We study them anyway, using approximation, using numerical methods, using whatever tools apply. The space of all continuous functions is vast beyond comprehension, the space of functions we can write down explicitly, using standard notation and operations, is infinitesimally small in comparison. Yet it contains remarkable richness, enough to occupy mathematicians indefinitely. Consider now the operation of taking limits, central to calculus and analysis. The sequence converges to a limit if, beyond some point, all terms are arbitrarily close to the limit value. A function approaches a limit, as x approaches some value, if the function values get arbitrarily close to the limit, when x is sufficiently close. Limits formalize the intuitive notion of approaching something. They make rigorous the idea of continuity, of smoothness, of all the calculus concepts we use. Without limits, we cannot define derivatives or integrals precisely. Without them, we cannot discuss convergence of series or solutions of equations. The epsilon delta definition of a limit captures this precisely. We say the limit of f of x as x approaches a equals L. If for every epsilon greater than 0, there exists a delta greater than 0, such that whenever 0 is less than the absolute value of x minus a, which is less than delta, we have the absolute value of f of x minus L is less than epsilon. This definition is technical, but it's necessary for rigor. It says that by making x close enough to a, we can make f of x as close to L as we want. The challenge is that how close x needs to be depends on how close we want f of x to be, captured by delta depending on epsilon. For simple functions like polynomials, proving limits using this definition is straightforward. For more complex functions, it can be difficult. But once we establish basic properties, like the limit of a sum being the sum of limits, we can build up to complex cases without returning to first principles each time. The exponential function e raised to x is continuous everywhere, meaning the limit as x approaches any point equals the function value at that point. This continuity extends to the complex plane. E raised to z is entire, analytic everywhere, infinitely differentiable. The function e raised to x is also continuous everywhere on the real line, and entire in the complex plane. Compositions of continuous functions are continuous. Compositions of analytic functions are analytic. The properties propagate. But consider the function that equals e raised to x for rational x and equals 0 for irrational x. This function is discontinuous everywhere. At every point there are nearby rationals and irrationals, so the function jumps. Yet it's well defined, a legitimate function from reals to reals. Such pathological functions, discontinuous everywhere, challenge our intuition. They can't be graphed in any meaningful sense. They can't be integrated in the usual Riemann sense. They're not the functions we encounter in applications, but they exist, and understanding them clarifies the boundaries of our concepts. The Dirichlet function, 1 on rationals and 0 on irrationals, is the classic example. It's measurable and Lebesgue integrable, integrating to 0 since the rationals have measure 0. But it's not Riemann integrable, because upper and lower sums don't converge to the same value. Lebesgue integration extends Riemann integration by changing what we consider measurable. Instead of partitioning the domain into intervals, we partition the range into values and measure the preimages. This allows integration of functions that are too discontinuous for Riemann. Measure theory, the foundation of modern integration, assigns sizes to sets in a way that extends length, area, volume. Not all sets are measurable. At least not if we want measure to have reasonable properties. But the measurable sets include all sets we can construct without exotic set-theoretic tricks. On the measurable sets, we can define integration as expected value and probability, as area under curves in geometry, as averages in analysis. The integral becomes a flexible tool, applicable far beyond its original context of computing areas. The exponential function, being continuous, is certainly measurable and integrable over any finite interval. The integral of e raised to x from a to b equals e raised to b minus e raised to a. Over the entire real line, the integral diverges, being infinite in one direction. For e raised to x, the integral over any finite interval exists, and can be approximated numerically. The integral from negative infinity to 0 is finite, since the integrand approaches 1, as x approaches negative infinity, and decays quickly for moderately negative x. The integral from 0 to infinity diverges, since the integrand grows faster than any exponential. These integral properties connect to probability distributions. A function can be a probability density if it's non-negative and integrates to 1. The exponential distribution, with density lambda times e raised to negative lambda x for x greater than 0, is a standard probability model for waiting times. The double exponential, or Laplace distribution, with density 1/2 times lambda times e, raised to negative lambda times the absolute value of x is symmetric and has heavier tails than the Gaussian. It models data with occasional large deviations. A distribution based on e raised to x would have extremely heavy tails, concentrating most mass near the mode, but having probabilities that decay doubly exponentially, rather than exponentially. Such distributions appear in extreme value theory, modeling the maximum of many samples. The Gumbel distribution, used for maxima, has cumulative distribution, function e raised to negative x. Its density is e raised to negative x times e raised to negative e raised to negative x, involving both the exponential and its composition. This appearance of nested exponentials in probability is not coincidental. Extreme values, rare events, tail behavior, all push us beyond simple exponential decay into regimes where iterated exponentials dominate. Risk analysis, reliability engineering, climate modeling, all deal with extremes. What's the probability of a flood exceeding a certain level? What's the expected lifetime of a system with multiple failure modes? Questions like these require distributions that capture tail behavior accurately. The mathematics of rare events is subtle. Small changes in assumptions can lead to large changes in predictions. Extrapolating from observed data to unobserved extremes is fraught with uncertainty. Yet decisions must be made, designs must account for worst cases, risks must be managed. Exponential functions, being the canonical model for decay and growth, serve as baselines. Deviations from exponential behavior signal different mechanisms, different physics, different underlying processes. A faster than exponential decay might indicate a finite time singularity. A slower than exponential growth might indicate saturation effects. The logistic function, 1 divided by 1 plus e raised to negative x, transitions smoothly from 0 to 1, modeling saturation. Its derivative is the logistic function times 1 minus the logistic function, a simple equation that leads to the logistic differential equation for population growth. This equation, di over dx equals r times y times 1 minus y over k, says the growth rate is proportional to both the population and the remaining capacity. When y is small, growth is exponential. As y approaches the carrying capacity, k, growth slows, and eventually stops. The solution is a logistic curve, starting near 0, growing exponentially, then saturating near k. The inflection point, where growth is fastest, occurs at half the carrying capacity. This S-shaped curve appears in countless applications, from biology to economics to technology. Adoption. The logistic function is related to the hyperbolic tangent, another sigmoid function. Both are special cases of squashing functions used in neural networks, transforming arbitrary inputs into a bounded range. Neural networks inspired by biological neurons consist of layers of simple computational units. Each unit computes a weighted sum of inputs, applies a nonlinear activation function, passes the result to the next layer. Training adjusts the weights to minimize error on the dataset. The universal approximation theorem states that a neural network with a single hidden layer can approximate any continuous function arbitrarily well, given enough units. This is a powerful existence result, but doesn't tell us how to find the weights or how many units are needed. In practice, deep networks with many layers often perform better than shallow networks, capturing hierarchical structure and data. The composition of many simple nonlinearities can represent complex functions compactly. Exponential functions appear in neural networks through the softmax function, which converts a vector of scores into probabilities. The probability of class I is e raised to the score I divided by the sum of e raised to score j over all classes j. This ensures probabilities are positive and sum to 1. The exponential amplifies differences between scores, making the highest score dominate. This is useful for classification, selecting the most likely class, but can lead to overconfidence. The cross-entropy loss function, used for training classification networks, involves the logarithm of predicted probabilities. Minimizing cross-entropy encourages the network to assign high probability to correct classes. The gradient of this loss with respect to the scores has a particularly simple form when using softmax. These connections between exponentials, logarithms, probabilities, and optimization are fundamental to modern machine learning. Gradient descent, the algorithm for training networks, follows the negative gradient of the loss function, taking steps in parameter space to reduce error. The gradient itself involves derivatives, back-propagated through the network using the chain rule. Each layer's contribution to the gradient depends on the derivatives of its activation functions. Exponentials, with derivatives equal to themselves, have particularly simple gradients. Deep networks can suffer from vanishing or exploding gradients. If derivatives are small, gradients diminish exponentially with depth, making early layers train slowly. If derivatives are large, gradients explode, causing instability. Careful initialization and architecture design mitigate these issues. Skip connections, allowing signals to bypass layers, help gradients flow. Normalization, rescaling activations to have mean 0 and variance 1, stabilizes training. Residual networks, building deep architectures from blocks with skip connections, can be trained to hundreds or thousands of layers. These engineering solutions to mathematical challenges show how theory and practice inform each other. The mathematics of optimization, gradients, convergence provides insight. The empirical experiments reveal which techniques work. Together, they push capabilities forward. Returning to the function e raised to x from this perspective, we might ask whether it appears in neural networks or machine learning. Not prominently, but the principle of composition, building complex functions from simple ones, is central. Each layer of a network is a composition. The overall function computed by a deep network is a composition of compositions, an iterated transformation. While individual layers typically don't use nested exponentials, the overall architecture embodies the idea that iteration creates complexity. In recurrent neural networks, which process sequences, the same transformation is applied repeatedly at each time step. The hidden state evolves according to a recurrence relation similar to iterating a function. If the transformation involves exponentials, the iterated effect can resemble nested exponentials. Long short-term memory networks, a type of recurrent network, use gating mechanisms involving sigmoids and hyperbolic tangents to control information flow. These functions, related to exponentials, modulate what information is remembered or forgotten at each step. The dynamics of these networks, especially over long sequences, to be complex. Information can be stored, retrieved, transformed in intricate ways. The space of possible computations is vast, limited mainly by the number of parameters and training data available. Training these networks involves optimizing over a high-dimensional parameter space, often millions or billions of dimensions. The loss landscape, the surface defined by loss as a function of parameters, is incredibly complex, full of local minima, saddle points, plateaus. Yet gradient descent works surprisingly well in practice. The high dimensionality helps, providing many directions to move. Stochasticity, using random subsets of data for each update, adds noise that can escape shallow minima. Momentum, accumulating gradient information over time, accelerates convergence. The success of deep learning, training these complex models to perform tasks that seemed impossible a decade ago, is one of the great empirical achievements of recent mathematics and computer science. The theory lags behind practice in many ways. We know these methods work, but don't fully understand why. This gap between empirical success and theoretical understanding is not unique to machine learning. It appears throughout applied mathematics, physics, engineering. We use methods that work, refining them through experience, even when rigorous justification is lacking. Eventually, theory catches up, providing explanations, generalizations, guarantees. The development of mathematics has always involved this interplay between concrete problems and abstract theory, neither proceeding independently, each forming and motivating the other. The exponential function, from its origins in compound interest and population growth, has become central to vast areas of mathematics. It appears in calculus as the function that's its own derivative, in complex analysis as the function that's periodic in the imaginary direction, in linear algebra as the matrix exponential connecting continuous and discrete systems, in probability as the basis for countless distributions, in differential equations as the fundamental solution to constant coefficient equations. Nested exponentials extend this ubiquity to more specialized contexts. They model faster than exponential growth in combinatorics, complexity theory, and nonlinear dynamics. They appear as solutions to certain transcendental equations, in asymptotic expansions of special functions, in the analysis of algorithms. Understanding these functions requires tools from multiple areas of mathematics: series expansions from analysis, polynomial approximations from numerical methods, differential equations from applied mathematics, complex variable techniques from complex analysis. Each lens reveals different aspects, different properties, different applications. The journey from simple exponentials to nested exponentials to general compositions illustrates how mathematics builds complexity. From simplicity, how iteration and combination create richness from basic building blocks. This is the essence of mathematical thinking. Start with simple objects, well understood and tractable. Combine them, transform them, study the results. When the results are simple, understand them completely. When they're complex, develop tools to analyze them approximately, asymptotically, numerically. Always there's the tension between exact and approximate, between symbolic and numeric, between finite and infinite. We want exact answers, but often approximate ones suffice. We want symbolic expressions, but numerical values might be all we need. We imagine infinite processes, but we compute with finite steps. Mathematics mediates these tensions, providing frameworks for rigor while accommodating approximation, enabling symbolic manipulation while grounding it in computation, defining infinite objects while relating them to finite constructions. The exponential function, in all its forms, exemplifies this mediation. It's defined as a limit, an infinite series, but we compute it with finite sums. It's an exact solution to differential equations, but we often approximate those solutions numerically. It's a transcendental function, beyond algebra, but we understand it through polynomial approximations. In studying e raised to x, we're not just studying one peculiar function. We're exploring how mathematics handles complexity, how tools developed for simple cases extend to harder ones, how rigorous theory and practical computation work together. The function is simple to write, two symbols and a variable. But its behavior is rich, its analysis requires sophisticated tools, its properties connect to deep areas of mathematics. This is typical. Simple expressions can have complex implications. The challenge and joy of mathematics lie in unraveling these implications, discovering what's hidden in what seems obvious, finding structure in apparent chaos. Looking at the path we've traced so far, we arrive at something that feels almost inevitable. Exponentials have threaded through everything, sometimes visible, sometimes hiding beneath other structures. Now we turn to face them directly, to see what they reveal when we stop treating them as tools, and start treating them as landscapes worth exploring on their own terms. The exponential function sits at a strange intersection. It's growth incarnate, the mathematical expression of compounding, of things building on themselves. Start with 1, multiply by some base repeatedly, and you get exponential growth. 1 becomes 2, becomes 4, becomes 8. The pattern is relentless, mechanical even, yet it describes so much of what happens in the world. Populations grow exponentially when resources are unlimited. Radioactive decay follows exponential curves downward. Money compounds. Epidemics spread. The pattern appears everywhere we look. But there's something deeper happening. The exponential function isn't just about repeated multiplication. It's the unique function that equals its own derivative, the function that changes at a rate proportional to its current value. This property makes it fundamental to calculus, to differential equations, to any situation where how fast something changes depends on how much of it there is. When we write e raised to x, we're invoking a specific base, the number e, approximately 2.71828. This number appears naturally when we ask what base makes the derivative of the exponential function equal to the function itself. With any other base, say 2 raised to x, the derivative is a constant multiple of the function. Only with base e does that constant equal exactly 1. The number e itself emerges from a limit. Consider the expression 1 plus 1 over n raised to the n power. As n grows, this expression approaches e. When n equals 1, we get 2. When n equals 10, we get about 2.59. When n equals 100, we get about 2.705. The limit as n goes to infinity is e exactly. This limit has a beautiful interpretation. Imagine interest compounding on the loan. If the annual interest rate is 100%, and it compounds once per year, you get 1 plus 1 equals 2 times your original amount. If it compounds twice per year at 50% each time, you get 1 plus 1/2 squared equals 2.25. If it compounds n times per year at 1 over n per period, you get 1 plus 1 over n raised to n. As the compounding becomes continuous, happening every instant rather than at discrete intervals, the growth factor approaches e. So e is the natural base for continuous compounding. It's what you get when growth is perfectly smooth, when changes happen infinitesimally, rather than in chunks. This makes it the right base for modeling continuous processes, which is most of what we actually care about in science and engineering. The function e raised to x has remarkable properties beyond being its own derivative. It's always positive, never crossing zero. As x goes to negative infinity, the function approaches 0 from above. As x goes to positive infinity, it grows without bound. The curve is smooth, increasing everywhere, ending upward in that characteristic exponential curve. We can extend the exponential to complex numbers. What does e raised to I mean, where I is the square root of -1? Euler's formula provides the answer. E raised to I times theta equals cosine theta plus I times sine theta. This connects the exponential function to trigonometry in a profound way. When theta equals pi, we get e raised to I times pi equals cosine pi plus I times sine pi equals -1 plus 0 equals -1. Rearranging gives e raised to I times pi plus 1 equals 0. Euler's identity, often called the most beautiful equation in mathematics, that links 5 fundamental constants, e, I, pi, 1, and 0. This complex exponential rotates around the unit circle in the complex plane. As theta increases, e raised to I times theta traces a circle of radius 1, moving counterclockwise. The exponential function, which seemed purely about growth, becomes about rotation when we pass to complex numbers. For general complex e equals x plus I times y, we have e raised to z equals e raised to x times y equals e raised to x times c raised to I times y equals e raised to x times the quantity cosine y plus I times sine y. The magnitude is e raised to x, depending only on the real part. The phase is y, depending only on the imaginary part. The complex exponential separates growth from rotation. This makes the exponential function the right tool for describing oscillations. The damped oscillation, something vibrating while gradually losing energy, has the form e raised to negative a times t times cosine omega times t, where a is the damping coefficient and omega is the frequency. We can write this using complex exponentials as the real part of e raised to negative a plus I times omega times t. Differential equations governing oscillating systems naturally involve exponentials. The equation for a harmonic oscillator, d squared x over dt squared plus omega squared x equals 0, has solutions that are sines and cosines, but these are really just combinations of e raised to I times omega times t and e raised to negative I times omega times t and e raised to negative I times omega times t. The exponential form often makes calculations cleaner. When we add damping, getting d squared x over dt squared plus 2 times b x dn's dt plus omega squared x equals 0, the solutions involve exponentials multiplied by exponentials. If b is less than omega, we get damped oscillations. E raised to negative b times t times cosine square root of omega squared minus b squared times t. If b equals omega, we get critical damping, a pure exponential decay without oscillation. If b is greater than omega, we get overdamping, a sum of two exponentials with different decay rates. All of these behaviors emerge from the fundamental property that exponentials are eigenfunctions of differentiation. When we assume a solution of the form e raised to lambda times t and substitute into the differential equation, we get an algebraic equation for lambda. Solving that algebraic equation tells us which exponentials appear in the solution. This eigenfunction property extends to partial differential equations. The heat equation, describing how temperature diffuses through a material, is dt over dt equals alpha times d squared t over dx squared. Separating variables, assuming t of x and t equals x of times tau of t, we get tau equals e raised to negative alpha times k squared times t, and x is a combination of sines and cosines, with spatial frequency k. The general solution is a sum over all frequencies, each frequency decaying exponentially in time, at a rate proportional to its square. High frequencies die out quickly. Low frequencies persist. Eventually everything smooths to a uniform temperature. The wave equation, d squared u over dt squared equals c squared times d squared u over dx squared, has solutions that combine exponentials differently. We get u of x, then t, proportional to e raised to I times k, times x, times e raised to plus or minus I, times omega times t, or omega equals c times k. These are traveling waves, patterns moving through space at speed c. Both equations, heat and wave, have exponentials at their core. The difference is whether time appears linearly or quadratically in the equation. Linear time gives oscillation and propagation. Quadratic time gives diffusion and decay. Now consider what happens when we compose exponentials with themselves. The function e raised to x is one such composition. We could also consider e raised to x is one such composition, or x, or any more variations. Each creates different behavior. The function e raised to x grows faster than any polynomial, faster than any single exponential, faster than anything we can easily imagine. When x equals 0, the value is e raised to 1, which is e. When x equals 1, the value is e raised to e, roughly 15.15. When x equals 2, the value is e raised to e squared, roughly 17,000. When x equals 3, we're already in the millions. This is sometimes called double exponential growth or tetration of order 2. It makes ordinary exponential growth look almost linear by comparison. In practical terms, such functions rarely appear in physics, because nothing in the real world can grow that fast for long. But they appear in complexity theory, in certain combinatorial problems, in places where we're counting abstract possibilities, rather than physical quantities. The derivative of e raised to x involves the chain rule. We get e raised to x times e raised to x. The inner function e raised to x has derivative e raised to x. The outer function e raised to u has derivative e raised to u. To multiply them together, the result is e raised to x times e raised to x, which we can also write as e raised to the quantity x plus e raisedness. This derivative is itself growing double exponentially. It grows even faster than the original function in a certain sense. The ratio of the derivative to the function is e raised to x, which is increasing exponentially. This means the function is accelerating exponentially. Not only is it growing, but the rate at which it's growing is itself growing exponentially. Higher derivatives compound this effect. Second derivative is e raised to x times e raised to x times the quantity 1 plus e raised to x. The third derivative involves more terms, all growing at comparable rates. Each differentiation multiplies by another factor, that's roughly e raised to x, for large x. Integrating e raised to x, as we've noted before, produces no elementary closed form. The antiderivative exists, must exist as a matter of calculus, but cannot be expressed using familiar functions. We can write it as the integral from 0 to x of e raised to t with respect to t, which is correct, but doesn't simplify further. We could expand as a Taylor series and integrate term by term. The series for e raised to x starts with e raised to 1 plus e raised to 1 times the quantity x minus 1 plus e raised to 1 times the quantity x minus 1 squared over 2 factorial plus e raised to 1 times the quantity 2 plus 1 times the quantity x minus 1 cubed over 3 factorial. The pattern continues growing more complex. Integrating term by term gives us a series for the antiderivative. The constant term e raised to 1 integrates to e raised to 1 times x. The linear term e raised to 1 times the quantity x minus 1 integrates to e raised to 1 times the quantity x minus 1 squared over 2. Each term integrates straightforwardly as a polynomial in x minus 1. This series representation is valid in some neighborhood of x equals 1. It converges for x near 1, though how near depends on the function's behavior. For large x, the series doesn't help much because the convergence is too slow. We'd need other methods, asymptotic expansions or numerical integration, to evaluate the antiderivative far from the expansion point. The broader lesson is that composition creates complexity. The exponential function by itself is tractable, well understood, easy to work with, but nesting exponentials, even once, produces something qualitatively more difficult. Twice tripling exponentials to create e raised to x makes things even worse. There's a hierarchy of growth rates. Polynomials grow according to their degree. Linear functions grow slowest, then quadratic, cubic, and so on. Exponentials grow faster than any polynomial. Double exponentials grow faster than any single exponential. Triple exponentials faster still. This hierarchy continues indefinitely. At the other end, inverse functions decay instead of grow. The natural logarithm, the inverse of the exponential, grows slower than any positive power of x. The function log x grows slower still. These ultra-slow growing functions appear in complexity theory, measuring how efficiently certain algorithms perform. Between growth and decay sits a balance point. Functions that grow exactly fast enough to stay bounded, but not so slow as to go to zero. These are the borderline cases, often the most interesting. They include things like x raised to the 1 over x power, which peaks at x equals e, and then slowly decreases. The exponential function's domain and range are worth examining closely. For real numbers, the domain is all real x, and the range is all positive real numbers. Every positive number can be expressed as e raised to something. If you want to get 10, you raise e to the natural log of 10, which is about 2.303. If you want 1/2, you raise e to negative natural log of 2, which is about negative 0.693. The natural logarithm is the inverse function of the exponential. It undoes exponentiation. If y equals e raised to x, then x equals natural log of y. The logarithm takes positive numbers and returns their exponents. It converts multiplication into addition. The natural log of a times b equals natural log of a plus natural log of b. This property makes logarithms useful for understanding multiplicative processes. The graph of natural log of x is the reflection of e raised to x across the line y equals x. It passes through the point 1, 0, since e raised to 0 equals 1. It increases everywhere but very slowly. As x approaches infinity, natural log of x approaches infinity too, but much more gradually than x itself grows. The derivative of natural log of x is 1 over x. This inverse relationship, where the exponential's derivative is itself, and the logarithm's derivative is 1 over the input, reflects their inverse nature. Composing them in either order gives the identity function, at least when domains are respected. For complex numbers, both functions become multivalued, or require branch cuts. The exponential e raised to z is single-valued for complex z, taking every non-zero complex value infinitely many times, due to the periodicity in the imaginary direction. But the logarithm of a complex number is not unique. If z equals e raised to w, then z also equals e raised to w plus 2 pi I times n, for any integer n. We choose a principal branch of the logarithm, typically taking the imaginary part between negative pi and pi. This makes log single-valued on the complex plane, minus the negative real axis. But crossing that branch cut causes the logarithm to jump discontinuously. This is a general feature of inverse functions in the complex plane. They tend to be multivalued unless we restrict their domains carefully. The square root has 2 values, the cube root 3 values, the nth root n values. The logarithm has infinitely many values, spaced 2 pi I apart. These multiple values are not errors or ambiguities. They're genuine features of the complex structure. Each value is equally valid mathematically. Which one we use depends on context, on which branch we've chosen to work with. The complex exponential connects to power series in a direct way. We've written e raised to z equals the sum from n equals 0 to infinity of z to the n over n factorial. This series converges for all complex z, making the exponential an entire function, analytic everywhere in the complex plane. The radius of convergence is infinite. No matter how large z gets, the series still converges, because factorials in the denominators grow faster than any polynomial in the numerator. This rapid growth of factorials ensures convergence. Other exponential type functions have finite radii of convergence. The function 1 over the quantity 1 minus z equals the sum from n equals 0 to infinity of z to the n converges only for the magnitude of z less than 1. This geometric series diverges outside the unit circle. The 1 over 1 minus z is a rational function, not an exponential. Its singularity at z equals 1 prevents it from being entire. The exponential has no singularities anywhere in the finite complex plane. Its only singularity is at infinity, and that's an essential singularity, a point where the function's behavior is maximally wild. Near an essential singularity, an analytic function takes on every complex value, infinitely often, in every neighborhood, with at most one exception. For the exponential, the exception is 0. Every other complex number is achieved infinitely many times near infinity. This is Picard's great theorem, a remarkable result. It says that essential singularities are truly singular, fundamentally different from poles or removable singularities. The function doesn't just blow up, it thrashes around in the complex plane, hitting almost everything infinitely many times. For e raised to z, the behavior is even more extreme. This function also has an essential singularity at infinity, and it too takes on every complex value except 0 infinitely many times near infinity. But because it's a composition of exponentials, its behavior is doubly wild in some sense. The modulus, the absolute value of e raised to z, depends on the real part of e raised to z. If z equals x plus I times y, then e raised to z equals e, placed to x times e raised to I times y, with modulus e raised to x. So e raised to z has modulus e raised to x times cosine y. For fixed x, as y varies, cosine y oscillates between -1 and 1. So e raised to x times cosine y varies between -e raised to x and e raised to x, meaning the modulus of e raised to e raised z varies between e raised to -e raised to x and e raised to e raised to x. This is an enormous range once x is even moderately large. When x equals 3, e raised to x is about 20, so the modulus varies between e raised to -20, which is tiny, and e raised to 20, which is huge. The function oscillates wildly in magnitude as we move in the imaginary direction. The phase, the argument of e raised to e raised to z, is similarly complex. It depends on the imaginary part of e raised to z, which is e raised to x times sine y. This winds around as y increases, creating spiraling behavior in the complex plane. Visualizing this function requires thinking carefully about what we want to see. We could plot the magnitude as a surface over the complex plane, watching it grow and oscillate. We could use color to represent phase, creating a domain coloring. We could trace curves where the magnitude is constant, or where the phase is constant. Each visualization reveals different aspects. The magnitude plot shows the exponential growth in certain directions, and the oscillation in others. The phase plot shows the winding and spiraling. Together they give a sense of the function's rich structure. But no single picture captures everything. This is a function from two real dimensions, the complex plane, to two more real dimensions, the complex output. We're trying to visualize four-dimensional information, which requires choices about what to project or slice or color. One approach is to fix the imaginary part of the input, then plot the output as the real part varies. Or fix the real part, then vary the imaginary part. Or trace the image of various curves in the input plane. Each choice gives partial information. The exponential functions collection to differential equations extends far beyond simple examples. Consider the matrix exponential, defined for square matrices in analogy with the scalar exponential. If A is a matrix, we define e raised to a as the sum from n equals 0 to infinity of a to the n, power over n factorial. This series converges for any matrix, just as the scalar series converges for any complex number. The matrix exponential has properties similar to the scalar exponential. If a and b commute, meaning a times b equals b times a, then e raised to a plus b equals e raised to a times e raised to b. The matrix exponential is the solution to systems of linear differential equations of constant coefficients. If dy over dt equals a times y, or y is a vector and a is a constant, matrix the solution is y of t equals e raised to a times t times y of 0. To compute e raised to a times t, we can diagonalize a if possible, finding matrices p and d such that a equals p times d times b inverse, where d is diagonal. Then a to the n equals p times d to the n times p inverse. And the series for e raised to a becomes e raised to a equals p runs to e times t inverse to c. D is diagonal. Since d is diagonal, e raised to a is just the diagonal matrix with e raised to each diagonal entry of d. This reduces the matrix exponential to scalar exponentials of the eigenvalues. If a can't be diagonalized, we use the Jordan normal form, which is almost diagonal, with ones just above the diagonal, in certain places. The exponential of a Jordan block involves not just exponentials, but also polynomials times exponentials. All of this machinery exists to solve differential equations. The abstract structure mirrors the concrete calculations we do for scalar equations. Eigenvalues of the matrix play the role of the constants lambda in scalar equations. Eigenvectors give the direction of exponential growth or decay. In physics, these matrix exponentials describe quantum time evolution. Schrödinger equation, I times d psi over dt equals h times psi, as solution psi of t equals e raised to negative I times h times t times psi of 0, where h is the Hamiltonian operator. For finite-dimensional systems, this is a matrix exponential. The Hamiltonian's eigenvalues are the energy levels. The eigenvectors are the stationary states. The time evolution operator e raised to negative I times h times t rotates the state vector in Hilbert space, creating the dynamics of quantum mechanics. So exponentials are not just mathematical abstractions. They describe how systems evolve in time, how waves propagate through space, how quantum states interfere and decohere. They're the functions of change, of dynamics, of becoming. Let's return to growth rates and comparisons. We've said exponentials grow faster than polynomials. More precisely, for any polynomial p of x and any exponential e raised to a times x with a positive, the ratio e raised to a times x over p of x goes to infinity as x goes to infinity. This means that eventually, no matter how large the degree of the polynomial or how large its coefficients, the exponential overtakes it and grows faster. The polynomial might leave for mean a while if it has huge coefficients or very high degree, but asymptotically exponential wins. Similarly, logarithms grow slower than any positive power. The ratio natural log of x over x raised to epsilon goes to 0 as x goes to infinity for any epsilon greater than 0, no matter how small. Logarithms grow, but barely, compared to power functions. Between polynomials and exponentials sits a rich landscape of intermediate growth rates. Functions like x raised to natural log of x, which is also e raised to natural log of x, times natural log of x, grow faster than any polynomial, but slower than any exponential. These superpolynomial but sub-exponential functions appear in complexity theory, particularly in factoring algorithms. There are even finer distinctions. The function e raised to the square root of natural log of x grows faster than any polynomial, but slower than any exponential. It's in a class called sub-exponential. Algorithms with this running time are faster than exponential but not polynomial. The hierarchy of growth rates is densely ordered. Between any two growth rates we can find infinitely many intermediate ones. This makes classification tricky. Resort to asymptotic notation, saying a function is big O of another if it grows at most as fast, or big omega if at least as fast, or big theta if they grow at the same rate up to constant factors. These notations let us compare algorithms and functions without getting bogged down in exact formulas. We care about long-term behavior, about what happens as inputs get large, not about small inputs where everything is fast anyway. Exponentials also appear in probability and statistics. The normal distribution, the bell curve, has probability density proportional to e raised to negative f squared over 2. This exponential of a quadratic creates the characteristic shape, peaking at 0 and falling off rapidly in both directions. The normal distribution is ubiquitous because of the central limit theorem. Sums of many independent random variables, regardless of their individual distributions, tend toward normality as the number of terms increases. The exponential function emerges from this limiting process. Other distributions involve exponentials too. The exponential distribution itself, used to model waiting times, has density a times e raised to negative a times x for a is positive. The Poisson distribution, counting rare events, has probabilities e raised to negative lambda times lambda to the k over k factorial. Exponentials and their relatives pervade probabilistic models. In information theory, the exponential appears in the definition of entropy and encoding theorems. If a message has probability p of occurring, its information content is negative natural log of p. Summing over all messages weighted by their probabilities gives entropy. The connection to exponentials is that entropy measures the exponent in the number of typical sequences. If we have n independent uses of a channel with entropy h, there are roughly 2 raised to n times h typical sequences. The exponential function converts entropy to account. Maximum entropy distributions, those that make the fewest assumptions given constraints, often involve exponentials. If we know only the mean, the maximum entropy distribution is exponential. If we know the mean and variance, it's normal. These distributions maximize randomness subject to what we know. Shannon's noisy channel coding theorem says we can communicate reliably at any rate below channel capacity by using exponentially long codes. The probability of error goes to 0, exponentially fast in the code length. Exponentials govern how quickly we can make communication reliable. Now consider the function e raised to negative x. This is a decreasing exponential, approaching 0 as x goes to infinity, and approaching infinity as x goes to negative infinity. It's the mirror image of e raised to x, reflected across the vertical axis. Decreasing exponentials model decay processes. Radioactive decay follows this pattern. If you start with some amount of a radioactive substance, after time t, you have the original amount times e raised to negative lambda times t, where lambda is the decay constant. Half-life is the t when this equals 1/2, which occurs at t equals natural log of 2 over lambda. Cooling also follows exponential decay. Newton's law of cooling says the temperature difference between an object and its surroundings decreases exponentially over time. If T of t is temperature, and T sub s is surrounding temperature, then T of t minus T sub s equals the quantity T of 0 minus T sub s times e raised to negative k times t. Charging and discharging capacitors, drug concentrations in the bloodstream, atmospheric pressure, as a function of altitude all follow exponential patterns, some increasing, some decreasing, all reflecting a fundamental property that the rate of change is proportional to the current amount. The function e raised to negative x squared, without the division by 2, is the unnormalized Gaussian. Its integral from negative infinity to infinity is the square root of pi, a famous result. To normalize it, we divide by this integral, giving 1 over the square root of 2 pi times e raised to negative x squared over 2. This function decays faster than any exponential of x alone, because the exponent grows quadratically rather than linearly. It's sometimes called superexponential decay. By the time x reaches 3 or 4, the value is already negligibly small. Such rapid decay makes the Gaussian convenient for analysis. Almost all the probability mass sits near the center. Tails are negligible. We can truncate integrals at a few standard deviations without significant error. The Gaussian also has the nice property that its Fourier transform is another Gaussian. The transform of e raised to negative x squared is proportional to e raised to negative omega squared over 4. Self-similarity under Fourier transform makes Gaussians special, connecting time and frequency domains in a symmetric way. In quantum mechanics, Gaussian wave packets are the minimum uncertainty states, saturating the Heisenberg uncertainty principle. They're as localized as quantum mechanics allows, balancing position and momentum uncertainties. Multiplying two Gaussians gives another Gaussian. Convolving two Gaussians gives a Gaussian with variance, equal to the sum of the original variances. These closure properties make Gaussian processes mathematically tractable. But let's return to compositions and nestings. We've discussed e raised to x. What about x raised to x? This is also a superexponential function, though defined differently. For positive x raised to x equals e raised to x times natural log of x. As x increases from 0, x raised to x starts at the limit value 1, which requires some care to define. We take the limit as x approaches 0 from above. Let x raised to x equals the limit of e raised to x times natural log of x. As x approaches 0, natural log of x goes to negative infinity, but x times natural log of x goes to 0. So the limit is e raised to 0 equals 1. The function x raised to x decreases slightly from 1, reaching a minimum around x equals e to the negative 1, where the value is about 0.692. Then it increases, growing faster than any exponential, but slower than e raised to x. The derivative of x raised to x uses the technique of logarithmic differentiation. Let y equals x raised to x. Take the natural log of both sides. Natural log of y equals x times natural log of x. Differentiate both sides with respect to x. The left side gives 1 over y times dy over dx. The right side gives natural log of x plus x times 1 over x equals natural log of x plus 1. So 1 over y times dy over dx equals natural log of x plus 1, which means dy over dx equals y times the quantity natural log of x plus 1 equals x raised to x times the quantity natural log of x plus 1. This derivative is positive for x greater than e to the negative 1, confirming the function increases after its minimum. At large x, the derivative grows like x raised to x times natural log of x, which is nearly as fast as the function itself, indicating rapid growth. The function x raised to x is even more extreme. Here we have a tower of height 3. Evaluating at x equals 2 gives 2 raised to 2 raised to 2 equals 2 raised to 4 equals 16. At x equals 3, we get 3 raised to 3 raised to 3 equals 3 raised to 27, which is already in the trillions. Such rapidly growing functions appear in combinatorics, in counting certain structures or configurations. They also appear in theoretical computer science, measuring the complexity of certain algorithms, or the resources needed to solve certain problems. The inverse of these functions, the superlogarithms, or iterative logarithms, grow incredibly slowly. The function log star of x, the number of times you need to apply logarithm to reduce x to 1 or less, grows so slowly it might as well be constant for practical purposes. For x up to e raised to e raised to e raised to e, we have log star of x, at most 5. These ultra-slow growing functions appear in algorithm analysis. Some algorithms have running time proportional to n times log star of n, which is essentially linear for any realistic n. The log star is theoretically present but practically invisible. Between the extremes of super-exponential growth and super-logarithmic slowness lies the realm where most interesting functions live. Linear, quadratic, cubic growth, exponential, logarithmic, square root. These are the functions we encounter in applications, the ones that model real phenomena at human scales. But the extreme functions remind us of the breadth of possibility. Mathematics contains functions growing and decaying at every conceivable rate. The hierarchy is rich and infinite. No matter how fast a function grows, we can construct one that grows faster. No matter how slowly, we can construct one slower. This open-endedness is part of what makes mathematics inexhaustible. There's always something beyond what we've considered. Always another level of complexity or simplicity to explore. Let's think about the exponential from yet another angle, through generating functions. The generating function encodes a sequence as a power series. If we have sequence a 0, a 1, a 2, and so on, the generating function is the sum from n equals 0 to infinity of a sub n times x to the n. For the sequence of all 1s, 1, 1, 1, 1, the generating function is the sum of x to the n, which equals 1 over 1 minus x for the magnitude. At x less than 1, this geometric series is the simplest generating function. For the sequence in factorial, we get the sum of n factorial times x to the n. This series doesn't converge for any x not equal to 0 in the usual sense, but we can work with it formally, manipulating it algebraically without worrying about convergence. The exponential generating function of a sequence uses x to the n over n factorial, instead of just x to the n. For the sequence a sub n, this is the sum of a subs m times x to the n over n factorial. The exponential generating function of the sequence of all 1s is the sum of x to the n over n factorial equals e raised to x. So the exponential generating function of the sequence is all 1, 1, 1. This connects the functions to combinatorics. The nth coefficient, divided by n factorial, counts something related to permutations or arrangements. For the sequence in factorial, the exponential generating function is the sum of n factorial times x to the n over n factorial equals the sum of x to the n equals 1 over 1 minus x. So the ordinary generating function of factorials doesn't converge, but their exponential generating function is simple. These generating functions let us solve recurrence relations, count combinatorial objects, and translate between different representations of sequences. The exponential function appears whenever we're counting labeled structures, where the order of elements matters. In graph theory, the exponential generating function of connected graphs on n-labeled vertices involves the exponential function. The function e raised to x times the quantity e raised to e raised to x minus 1 minus x appears in formulas for counting various graph properties. These applications might seem far from the original conception of exponentials as growth functions, but they're united by the underlying mathematics. The exponential encodes information about factorials, about repeated operations, about structure building on itself. We could also discuss the exponential function's role in Fourier analysis more deeply. The Fourier transform takes a function f of x and produces the function f of omega equals the integral from negative infinity to infinity of f of x times e raised to negative I times omega times x with respect to x. This transform decomposes f into its frequency components. This function e raised to negative I times omega times x oscillates that frequency omega. Integrating f times this oscillation gives the amplitude of that frequency in f. The inverse Fourier transform reconstructs f from its frequency components. F of x equals 1 over 2 pi times the integral of f of omega times e raised to I times omega times x with respect to omega. These transforms are inverse to each other, up to constants. They convert between time and frequency, between position and momentum, between different representations of the same information. The exponential function, with its dual role as growth function and oscillation, is the kernel that makes this work. It's the eigenfunction of differentiation, the bridge between addition and multiplication via logarithms, the generator of rotations in the complex plane. All these roles stem from the single defining property, being equal to its own derivative. From this, everything else follows. The series expansion, the complex behavior, the connections to differential equations in Fourier analysis, all emerge from that one fact. In a sense, the exponential function is the simplest non-trivial function. Polynomials are simpler, but they don't capture dynamics. Constants are simpler still, but they don't capture change at all. The exponential is the first function that's truly alive, that embodies growth and change in a fundamental way. When we nest exponentials, creating towers of compositions, we're exploring how complexity emerges from simplicity. Each layer adds another level of indirection, another fold in the function's behavior. The result grows faster, oscillates more wildly, becomes harder to analyze. But even the most complex exponential composition is still built from the same simple pieces. It's still differentiable, still analytic where it's defined, still subject to the rules of calculus and complex analysis. The tools we use to understand simple functions still apply, though the calculations become more involved. This is a common pattern in mathematics. We start with simple objects and simple operations. We combine them in increasingly complex ways. The combinations inherit properties from the pieces, but exhibit new emergent behaviors. Understanding both the inheritance and the emergence is the challenge. Exponentials exemplify this pattern. They're simple in isolation, profound in combination, inexhaustible in variation. They connect discrete and continuous, algebraic and analytic, real and complex. They model growth and decay, oscillation and rotation, stability and chaos. In some ways, the entire edifice of calculus rests on exponentials. Derivatives and integrals, series and limits, differential equations and transforms, all involve exponentials at their core. Learning to work with exponentials is learning to work with change itself, and that's what calculus is ultimately about. Understanding how things change, how one quantity depends on another, how small differences accumulate into large effects, how local information determines global behavior. The exponential function, in its own derivative, is the fixed point of differentiation. It's the function that change doesn't change, that remains itself under the operator that measures change. This paradoxical stability, while embodying change, makes it central to the entire subject. As we've seen, even restricting to real numbers, exponentials are rich. Adding complex numbers multiplies that richness. The plane becomes a landscape of growth and rotation, magnitude and phase, zeros and poles, and essential singularities. Generalization opens new vistas. Matrix exponentials for systems of equations. Operator exponentials for quantum evolution. Exponential maps in Lie theory connect to algebra and geometry. The concept extends far beyond the elementary function we started with. Yet all these generalizations preserve the core property. Exponentials are the solutions to equations of the form derivative equals constant times function. In one dimension, scalar equations. In many dimensions, matrix equations. In manifolds, operator equations. The pattern persists across contexts. This universality suggests we're touching something fundamental about mathematics itself, not just about a particular function. The exponential represents something deep about how structures build on themselves, how recursive processes unfold, how symmetry and dynamics intertwine. In the end, studying exponentials is studying the mathematics of becoming, of process, of change. It's looking at the world not as static configurations, but as flows and transformations. This perspective pervades modern mathematics and physics, from dynamical systems to quantum field theory. The function e raised to x, simple as it appears, contains multitudes, its derivatives, its integrals, its series, its values. All tell us something about the nature of growth and change. When we compose it with itself, we see how complexity emerges from iteration. When we apply it to matrices or operators, we see how it organizes higher dimensional dynamics. Every time we encounter an exponential in mathematics, we're meeting an old friend in a new guise. The function might be wearing different clothes, might be playing a different role, but it's the same underlying structure. Recognizing it, understanding its properties, using it effectively, these are core skills in mathematical thinking. And beyond pure mathematics, exponentials shape how we understand the world. Population dynamics, compound interest, radioactive decay, electrical circuits, temperature change, all follow exponential patterns. Learning to recognize and work with these patterns is learning to think quantitatively about change. So while this exploration is focused on mathematical properties, the implications extend far beyond. Exponentials are tools for thought, frameworks for understanding, bridges between abstract theory and concrete application. The journey from e raised to x through e raised to x, and beyond traces a path from elementary to advanced, from simple to complex, from familiar to strange. But it's all continuous, all connected, all part of the same mathematical landscape. Understanding that landscape, being able to navigate it, seeing how different regions connect and differ, that's what mathematical maturity looks like. It's not about memorizing formulas or techniques, though those help. It's about seeing structure, recognizing patterns, understanding why things work the way they do. Exponentials offer a perfect case study in this kind of understanding. They're simple enough to grasp quickly, but deep enough to repay extended study. They appear everywhere, connect to everything, reveal new aspects the longer you look. This text has tried to capture some of that richness, to show exponentials from multiple angles, to trace connections between different appearances of the same underlying idea. The goal isn't exhaustive coverage, which would take volumes. It's to give a sense of the landscape, to point out interesting features, to encourage further exploration. Mathematics is infinite. We can never see all of it, but we can see enough to appreciate its structure, to navigate confidently within familiar regions, to venture into new territories with some idea of what to expect. Exponentials are an excellent region to know well. They're central, well-connected, beautiful in their own right. Spending time here, understanding the terrain, pays dividends throughout mathematics and beyond. As this section closes, the exponential function remains, as it has always been, fundamental and inexhaustible. Each encounter reveals something new. Each application shows another facet. The function that equals its own derivative, that bridges growth and rotation, that solves so many equations and models, so many phenomena, continues to surprise and enlighten.